Good morning. My name is Ala Kamil, and I am serving as the designated federal official to the U.S. EPA Science Advisory Committee on Chemicals, SAC. For this meeting, and in my role, I will be opening the second day of the public meeting on EPA's 2023 draft supplement to the 1,4-dioxane risk evaluation. I'd like to repeat that the SAC meetings are subject to all FACA requirements. These include open meetings, timely public notice of meetings, and document availability to the public. All documents are available to the public in the docket at regulations.gov. See docket number in the meeting agenda. Also, that this meeting is being webcasted, transcribed, and recorded. A live stream of today's meeting is available on YouTube. See the link on the meeting website, and it is also listed in the agenda. The website is listed in the agenda, which also has a link to yesterday's meeting. We had a successful opening day yesterday, and I would like to thank the SAC and the ad hoc reviewers, the EPA team for their presentations, and the public also for their public comments and all the discussions that we had yesterday. And now I will hand it over to the chair, Dr. George Cobb. George?
Thank you, Ala, and welcome everyone. I'd like to thank the EPA staff for making the great presentations yesterday and our public commenters as well. I think first of all, we should probably do our roll call, and then we will circle back to items from yesterday that may need further clarification. So first of all, let's take the roll. Dr. Apte?
Present.
Dr. Baker? Dr. Baker? Okay, Dr. Chasen?
Present.
Dr. Ike?
Present.
Dr. Fox?
Dr. Baker's here. I couldn't get off mute. Sorry, here.
That's okay. It happens to me too. Dr. Graham?
Here.
Dr. Hyger-Benace? Wendy here? No. Ms. Jenkins?
Here.
Dr. Merced Nieves?
Good morning. Here.
Dr. Messerling? Dr. Ottinger?
Here.
Dr. Presbilla?
Present.
Dr. Wright? Dr. Wright?
Here.
Thank you. Dr. Rubin?
Present.
Dr. Rumpler?
Present.
Dr. Voorhees? Dr. Wright?
I'm here.
Thank you. Dr. Bennett?
I am here. Good morning.
Dr. Barakal?
Here.
Dr. Clark?
Present.
Dr. Ginsburg?
I'm here.
Dr. Henneman?
Here.
Dr. Jajak?
Here.
Dr. McKenzie?
Here.
Dr. Miglino?
I'm here.
Dr. Portier?
Here.
Dr. Potter?
Good morning.
All right, so let me go back and see folks that might not have been able to get off mute. Dr. Hyger-Bernays? Dr. Messerling? Dr. Voorhees? Okay, so we've got the roll taken care of. Thanks for bearing with us on that nuance for the virtual meetings. I guess a couple of housekeeping issues. Dr. Jajak indicated that he wanted to make a general comment, and rather than have the potential for each and every one of us to make a general comment right now and throw our timing completely off for the entire day, and I'd like to ask folks, if you have general comments that can be worked into the charge question that you are answering, please do so. If you don't feel that it really fits in a charge question at all, then we will reserve time towards the end of the meeting to entertain those general comments, as well as we have time at the end of some days that we may do that as well. Also, we ended the day a bit early during the public comments topic, and one of the public commenters was actually traveling during yesterday and is available today. So before we get to any clarifications from the agency or from the SAC to the agency, we'd like to ask Dr. Sussman from the American Chemistry Council to make his public comment.
Thank you, Dr. Cobb. This is actually Steve Rosado from the American Chemistry Council.
You know what? I'm sorry. I got the wrong name. I wrote the wrong name down.
Yeah. Oh, not a problem. My apologies for not being available yesterday afternoon, and my sincere thanks for allowing me to address you this morning. I will be brief. My name is Steve Rosado, and I am a senior director at the American Chemistry Council, speaking today on behalf of ACC's 1,4-dioxane panel. The panel has been engaged in EPA's risk evaluation of 1,4-dioxane since it began in 2017, focusing on the agency's interpretation of the evidence for the carcinogenic potential of 1,4-dioxane. Although the agency has not asked the SAC to review the toxicology of 1,4-DX, it is important to note that the U.S. is at odds with much of the rest of the world in terms of assessing the carcinogenicity of 1,4 at low doses. While much of the rest of the world believe that there is a dose below which 1,4-dioxane does not pose a cancer risk, here in the U.S., we assume the default non-threshold model for cancer potential, such that any exposure is assumed to increase the risk of cancer. That assumption affects every risk comparison in the document that you have been asked to review. Setting aside the question of whether the non-threshold assumption is correct, EPA has asked for your expert opinion on its approach to assessing risks from occupational and fence line exposures to 1,4-dioxane as a byproduct of manufacturing processes or as a contaminant in products. For most of the occupational scenarios considered, however, the agency has very little data on exposure. In one case, the data amount to a single measurement. In practically all cases, the data are decades old, dating back as far as the 1980s. So one question you may want to address is whether it's appropriate for the agency to make risk determinations based on such limited and out-of-date information. You have heard from oral comments yesterday that contaminant levels of 1,4-dioxane in products have been reduced significantly in recent years. And while not every cleaning product meets the current New York State limit of 2 parts per million, current levels are well below the 4,000 parts per million present in some of the products included in the agency's evaluation of soaps and detergents. Shouldn't EPA's assessment be based on current levels of 1,4-dioxane in the products it chooses to evaluate, particularly when that information is readily available? For its fence line analysis, EPA had little or no information on ambient air or water levels of 1,4-dioxane around the facilities it analyzed. It was entirely dependent on modeling to estimate fence line exposures. The agency asked the panel to comment on whether the approaches and assumptions used for modeling are reasonable, but how can you make that determination in the absence of measured data to validate the result? EPA staff yesterday suggested strong concordance between measured and monitoring surface water concentrations. But that assertion requires your careful scrutiny since the comparisons are limited and not always in full agreement. For drinking water exposures, fortunately, there are data on 1,4-dioxane concentrations from the agency's UCMR3 National Survey of Public Drinking Water Sources. In that comprehensive survey, greater than 95% of the samples were below the level that generates a 1 in a million risk using EPA's default cancer assumption. As a result, EPA's Water Office deferred a determination on whether to establish a drinking water standard for 1,4 in 2021 because it could not conclude that there was a meaningful opportunity to improve public health. In 2022, staff from EPA's Office of Research and Development produced similar results after considering both drinking water levels and down the drain releases using the same SHEDS HT model used in the draft supplement. On what basis can the Toxics Office conclude anything different? One final note, EPA has proposed an existing chemical exposure limit, or ECHL, for 1,4-dioxane in occupational settings, but has not asked this committee for input. The document was recently added to the document for the draft supplement. Shouldn't the panel's review include consideration of the proposed ECHL? We encourage you to include these additional questions in your review. Thank you for your attention.
All right. Thank you for that comment. Are there questions from the committee to Dr. Risotto? If not, we can proceed to clarifications or follow-ups from yesterday's discussion. I think I'll first turn to the agency and see if there are questions that we pose to you that you have answers now, or if there are other items that you wanted to bring up. Do we have the EPA folks there?
Hi, can you hear me? This is Brian Groza.
Yes.
Okay. I do have a couple of clarifications to follow up with from yesterday.
You can come closer to the microphone.
How does that sound? Is that clearer?
Better.
Okay. So on one point was for the down the drain loading, the commercial loading values used were the 99th percentile of the distributions. There was an error in the slides shown yesterday that said 90th percentile. And that was one clarification. In Appendix G in the document, also related to the commercial and consumer down the drain loading, the commercial values reported in Table G2 are incorrect. They should reflect the 99th percentile values, which are in Table G4, which are correct. The consumer, the non-commercial values in Table G2 are correct. And for the distribution of finished drinking water samples that were shown, there were 14,228 samples. These were predominantly from the UCMR data set, so they cover all 50 states, and there were 2,827 unique public water system IDs in that data set. Thanks.
So thank you for those clarifications. And specifically, that last question was from me, and I probably should have asked it, is it in the, tens, hundreds, or thousands? But thank you for giving that exact number. So from the committee, are there further clarifications or questions that you have for the agency about anything that was presented yesterday? Okay, if not, I think we'll move into charge question 1. And I believe the agency should read that into the record, and then Dr. Cordier will lead that discussion.
Good morning. This is Franklin. I'm sorry. Put myself back on. Okay. Good morning. Can you hear me okay, Dr. Cobb?
Yes, I can.
Okay, excellent. So good morning, and this is Franklin Hall. I'll begin by reading charge question 1, specifically 1A. Comment on EPA's method for developing Monte Carlo modeling simulations and the use of those methods in the 1,4-dioxane draft supplement. Specifically, please provide detailed comments on the strengths, uncertainties, and the incorporation of variability.
Thank you for that. So Dr. Fortier is our lead discussant.
Thank you, Dr. Cobb, and good morning. Am I clear?
Yes.
Okay, thank you. So my presentation incorporates my comments as well as the comments submitted to me from Drs. Henneman and Ottinger before the start of the meeting. They may have developed additional comments or may wish to elaborate on these comments after my presentation. My line numbers, I'm going to quote specific line numbers, and these numbers refer to the document 14D Draft Supplemental Risk Evaluation, Internal Release, HeroNet, July 2023, because there have been a couple other copies going around. So this question requests the panel to comment on EPA's Monte Carlo methodology, both in creating the simulations and analysis, and also in using the methodology. In light of the request that yesterday that we helped finalize the report, some of these comments are specific to sections of the document presented to the panel for review. The goal of Appendix E 10, developing models that use Monte Carlo methods, is to describe the process of developing parts of a Monte Carlo simulation. The first thing the panel wondered is why EPA in this appendix makes no reference to key EPA documents where Monte Carlo methods are better described. Namely, these include EPA 1997, Guiding Principles for Monte Carlo Analysis, EPA 2014, Risk Assessment Forum White Paper, Probabilistic Risk Assessment Methods and Case Studies, and the National Research Council 2009, Science and Decisions, Advancing Risk Assessment. I think the addition of these documents that were pointed out to me by Dr. Fox would really help the reader of this section. The panel recommended changes to statements used to present the Monte Carlo methodology that clarify concepts and approaches and will improve the general discussion of Monte Carlo methodology in future documents. Some changes are minor word changes, which better describe what should be done. Other changes are in definitions that may be unclear in the draft document. For example, the definition of a stochastic process given on lines 7692 to 7702 needs to be improved. The panel recommended the following text. A stochastic or probability process has one or more inputs or parameters that can take values that are generated at random from a pre-specified probability distribution. The model outputs from randomly generated inputs are also random. The output from multiple runs of a stochastic model produces a distribution of values. Monte Carlo methods are a technique, not a replication technique. They're simply a technique for propagating uncertainty through a deterministic model. The deterministic model is run multiple times, each run based on input values that are drawn from a prescribed univariate or multivariate probability distribution. Random values from each run are generated independently of those of previous runs. Model outputs are collected, and the resulting distribution of output values is used to describe the probability or likelihood of that outcome value occurring. Next, figure APX E2 starting on line 7714, is not clear due to the black box aspect of the Monte Carlo add-in toolbox. Actually, all of the modeling steps are really performed within the Monte Carlo add-in tool. So the graph's really not a proper description of the approach. Next, replication is an essential component of good science. Use of freeware products is recommended in many Monte Carlo analysis situations since it allows others not directly tied to the development of the model to replicate the Monte Carlo analysis and also examine the implementation for mistakes. Section E10.3 should point out that when the deterministic model is fairly simple, the model can be described in a spreadsheet program, such as Microsoft's Excel, and that there are a number of software add-in products, such as Palisades, At-Risk, and Oracle's Crystal Ball, that simplify implementing the Monte Carlo process in an Excel spreadsheet. When the model is complex, which is often the case with, for example, pharmacokinetic, pharmacodynamic models, where the integration of a set of differential equations is required, a programming language with a set of built-in random number generators for a suite of probability distributions might be a better, more efficient choice for Monte Carlo implementation. Freeware tools such as R, Python have been successfully used in this case. Other popular Monte Carlo tools, though not free, are readily available, such as MATLAB from the MathWorks Incorporated and Gauss from Aptech Systems Incorporated, and others have also been used successfully. More discussion is needed on what is included in the label deterministic model. For the 1,4-dioxane, this risk assessment seems primarily concerned with modeling releases of chemicals to air, water, and soil. But there are also models that are used in other risk contexts that describe how the chemical of focus, once deposited on skin, inhaled, or ingested in food or water, gets translated into an exposure dose. A general discussion is needed of the components of a deterministic release model. Gleaning from sections E11 and E12, we find that these include a number of parameters, some but not all, that are potentially variable, such as daily rates, products used, products manufacturers, treated commercial goods, mass fractions, the amount of target chemical in product, residuals left in containers, etc., and facility operating parameters, operating days, container sizes, batch sizes, etc. So again, this is kind of since it's a general chapter on Monte Carlo methodology, I'm just saying these are kind of general statements that alert the reader to what kind of components should be found in a deterministic release model. The text can emphasize that most exposure and release deterministic models are what I would call an accounting model. That is, these models describe how much of the target chemical, in this case 1,4-dioxane, enters a facility, a manufacturing plant, a sewage treatment facility, a landfill, etc. How much of it is transformed within the facility, and then how much and in what form the chemical exits as a release in product and or as waste. Typically, there's only one point of entry, but there may be multiple points or places in the system where release can occur. The draft document's not always clear on why one model component, say one input parameter, is assigned to be a random variable and another is assigned to be a constant value. It may be obvious why one parameter is a constant, but in some cases, this is not so obvious. If a parameter that is obviously random, for example, varies over space or over time, but is assumed constant, the reason for that assumption needs to be clearly stated and justified. When a parameter is assumed to be random, the distribution needs to be identified so as whether it describes uncertainty in our knowledge of the true value of a constant for a facility, or it describes variability in parameter values over time for one facility, say temporal variability, or it describes variability in parameter values across the population of facilities, or spatial variability. I think making these descriptions is critical in understanding the results from a Monte Carlo analysis. There are a couple of places where word changes are needed to properly describe the process. So for example, in section E10 3.2, it uses the word define in describing how probability distributions get assigned to input parameters. The word define really should be replaced with the word assign when thinking about the process of linking a probability distribution to an input parameter. This may seem like a minor thing, but the word define kind of implies that there's one true distribution, whereas assign more correctly describes how one chooses among a set of candidate distributions the one we will assume for this assessment. It then reinforces the need to justify the distribution that's assigned. Next, I have a number of comments on the steps that they use to create a Monte Carlo process that's described in E10. So comments on step 1, which is labeled as select the model input parameters for which probability distributions will be developed. In step 1, the process is really one of identification rather than selection. Selection suggests a more subjective process than it really should be. Step 1 should be labeled as identify which model parameters will be treated as random and which as constant. There are reasons for how each model parameter is handled. In step 1, one needs to voice these reasons in an identification process. The discussion of step 1 that follows line 7737 attempts to discuss many of these common reasons: availability or lack of data, expert knowledge of the process, high or low variability in parameter values that translates to high or low sensitivity of the model to variability in this parameter. The availability of data to inform a distribution. The availability of data should not be the key decider of which parameters are considered random. Some model values are clearly random. They vary over time or over space or from location to location. Some model parameters will be clearly constant because of engineering constraints, regulatory constraints, etc. Model parameters that are clearly random, but for which measurement data are not available, may be treated as a constant or be assigned a probability distribution that's not necessarily data informed, but rather informed by querying experts. For example, using some sort of delta method, as in a Bayesian process, which many in EPA are very aware of. The discussion starting on line 7743 is good as far as it goes, but it needs to include much of what has been mentioned previously. A discussion of potential bias in the distribution provided by available data or information might be good to have here. If data is from one site, one type of process, or one location, it may not be truly representative of the full range of potential values for the model parameter. I should add to the list that if it's from one time point that is far removed from today, that may be another reason that the results may have a bias. It makes a difference whether the published distributional parameters come from a study with a few observations than from a study with many observations, even if the underlying observations are no longer available for our use. The concept of within site and between site variability should also be discussed when talking about random variables. If the parameter statistical distribution is meant to describe a typical site, then the distribution needs to be more of what statisticians would call a compound distribution, created by parameterizing the within site distribution and then assuming within site distributional parameters themselves might vary among sites and according to a different statistical distribution. For example, in the textile release model, we might assume the mean number of operating days within a site varies from 150 to 160 days with a mean of 155. Whereas another site has a mean number of operating days of, say, 160. The means themselves may vary from 50 to 200 days across the 783 sites that are discussed. Similarly, upper and lower bounds might vary from site to site. The next topic is the dependency of the input variables on one another. This statement covers two different situations. I should point out that the dependency of input variables on one another is a topic in E10. I'm just kind of reiterating on those topics. So one situation is where one quantity is derived from another. If a model parameter is derived from other input parameters, which themselves are random, the derived parameter is also random. Typically, you only assign a probability distribution to the base parameters, those that are on the right side of an equation, and not to the derived parameter. But when the derived parameter is a function of multiple random parameters, it's important to check the distribution of the derived parameter to determine whether it generates reasonable values. And that's kind of an intermediate part of a Monte Carlo process, making sure these distributions of derived parameters are reasonable. And this is probably a topic that's going to come up in question 1B as well. The second situation occurs when the two or more random variable input parameters covary. That is, their correlation is non-zero. But the relationship between the two is not exact. In other words, the correlation between the two is not equal to 1 or minus 1. In this case, we might have to assign a multivariate distribution to the set of random variables. Typically, this is done only if there's available data to inform this multivariate distribution. I make a note that creating multivariate distributions that are not normal or Gaussian, but which have correlation, can be quite difficult. A shortcut often used is to make one or more variables, is to move one of the variables from being random to being derived, and then add a little variability around the derived value. Essentially, one regresses one variable on the other and uses the regression line with uncertainty to describe the bivariate correlated values. Transformation and back transformation of variables may also be needed to get the needed distributions. The regression does not need to be linear. This is not often discussed in the Monte Carlo methodology, but it's quite effective for accommodating correlations in situations where the distributions are not normal. For example, when the distribution is, not normal, that is when the distributions are unimodal and symmetric. And I note that it may be difficult and challenging for me to find a good reference on this, but I will try to find one and add one to the report. For the example described starting on line 7756, it's not clear whether what is described is a set of jointly derived variables or a set of covarying random variables. So it is a situation of where the language is just not clear. A third topic is the sensitivity of the model results to input parameter values and distributional assumptions. Again, the focus in the report is on what the at-risk software can do, but all the other software tools that I mentioned previously can do this same analysis. It would be better to use the at-risk text as an example rather than suggest that this is the only way to do it. It's important that the assessment of parameter sensitivity be divorced from Monte Carlo analysis of parameter variability. Uncertainty characterization is appropriate in a higher tiered assessment. That is, it's typically done once parameter variability is properly incorporated into the model and results are analyzed. A sensitivity analysis needs to proceed according to a plan, with the goal being to estimate the potential consequences on the final models of the Monte Carlo analysis. Now I'll transition to comments on step 2, which is labeled determine a probability distribution. So the goal of step 2 uses the word determine. The process is really one of assigning rather than determining. Determining suggests that there's one real distribution, and the task is to determine what it is. Rather, as mentioned in lines 7807 to 7809, the process is one of choosing among a set of potentially candidate distributions, the one that best matches what we know from the data and or from expert knowledge. Standard statistical distributions, such as the uniform, the triangular, the normal, and the log normal, are nice in that they have mathematical forms that random variables can be fairly easily generated. But in the situation where we have a lot of available data, it is possible to let the data define the distribution. And there are tools and functions and modules available in the risk simulation packages and add-ins and program languages that facilitate sampling from such data-defined distributions, including sampling directly from the data using bootstrapping or jackknife techniques. As mentioned before, a mixture distribution may be required to describe the distribution, the situation. This may be the case where we know the underlying distribution is truly multimodal, or where there are a lot of, for example, below detect data values that need to be accounted for. For example, during the 160 days a facility may be processing product, there's also a large fraction of days that involve no product that involves the focus chemical. Hence, the distribution of the fraction of, say, dye may be 0 or 20% of the days, and then follow some distribution with a non-zero minimum for the other 80% of days. Now comments on step 3, check for and define statistical correlations. A better label for this step is evaluate and incorporate correlations among parameters where justified. In line 7839, I would replace setting with assigning statistical distributions. In line 7841, each parameter is assumed to be independent of all other parameters. The text needs to emphasize that this assumption needs to be justified, and if found to be invalid, the sampling methodology needs to accommodate sampling with correlation. Not accommodating correlations among model parameters can result in sets of parameters that are unlikely, that is, have low or no probability of occurring in practice. That is, they're not logical for the scenario as mentioned, and this is mentioned in the document. For example, starting in the middle of line 7842, the example starting in the middle of line 7842 that discusses the correlation among annual PV, daily PV, and operating days is well done. So this is a pretty good example. Line 7872, the text tells us that at-risk only uses the Spearman correlation coefficients, but does not describe how it uses this coefficient to generate correlated random variables. I suspect this is some sort of conditional sampling methodology, but I don't know, for example, does it work for non-normal distributed data? Does it work for bounded distributions? I really don't know the answer to this, but it should be described here if in fact this is how EPA wants it done. Comments on section E10 3.3, select model outputs for aggregation of simulation results. The draft supplements offers discussion on each of the inputs of the Monte Carlo methods, and in a few cases justifies the distributions assigned to random parameters and the values assigned to constants, but there's no discussion on the key outputs from the Monte Carlo assessment. Sections E10 3.3 should discuss how key assessment outputs are identified. And this may be as simple as pointing back to the deterministic model and saying, well, what we're really interested in are the environmental releases. The key model output, but the point I'm trying to make here is that they're not discussed and they're not pointed out as key assessment outputs in the discussion of the model building methodology. The key model outputs are typically statistics computed from select output parameters whose distributions result from running the deterministic model multiple times with varying inputs. In the three examples discussed in this report, it's implied that key output parameters are releases per day from the pre-identified release points. But really, what are discussed are statistics such as the mean daily release, the upper 95th percentile of daily release, the maximum daily release. But the Monte Carlo process will actually produce a time series when input parameters are themselves a time series. So other statistics, such as the number of days above some threshold release value, might be a key output whose distribution across runs might be of interest. If the input parameter represents spatial variability or total contiguous area having release concentration above some threshold, for example, might be a key parameter. The key parameters of interest need to be linked to the subsequent human health or environmental risk assessment. On a side note, to me, this is similar to the discussions that I've been in on these kinds of panels, where we look at maximum consumed dose, or we discuss whether it's maximum consumed dose or area under the curve or cumulative dose that's the biologically relevant exposure. So I think it's important here that in this discussion of key outputs that we talk about them as something like biologically or risk assessment relevant endpoints. And as I pointed out before, those running the Monte Carlo analysis need to remember that intermediate results typically need to be assessed as well. Consider, for example, in the textile dyeing example, the number of containers unloaded per site per year, which is a function of operating days, which is a random variable. The daily use rate of 1,4-dioxane per site per day, a random variable. A function of dioxane in the dye, a constant. The container size, a random variable. And the dye density, a constant. So it's important to examine the distribution of the number of containers unloaded per site per year to ensure that unreasonably high or low values are not being generated. Next, comments on E10 3.4, select simulation settings and run model. This discussion needs to be divorced from what at risk does. We need to discuss generic operative task, not how it's done in at risk. So the three operative tasks are setting the number of iterations, setting the sampling method, and the random number generation. So number of iterations, computational time is cheap, as was mentioned yesterday. And EPA set at 100,000 iterations were used because they produce stable mean estimates. But what happens if the key output parameter is not a mean? Often the goal of the Monte Carlo exercise is to understand the distribution of key model outputs, not just the average. In theory, one can get a decent, but maybe unstable estimate of, say, the upper 99th percentile with only 100 iterations, a very good estimate with 10,000 iterations, and a very stable estimate with 100,000 iterations. If examination of if the person running the Monte Carlo simulation examines a sorted list of output values and it shows a large number of repeated values, there's likely too many iterations are being used, and one can cut back on iterations in subsequent runs. A search of the statistical literature may provide a procedure for estimating the needed number of iterations to estimate an upper percentile to a given level of precision. I'll look for a reference on that. On the sampling method, it discusses the Latin hypercute as a type of stratified random sampling within a multi-dimensional space, whereas the Monte Carlo method is just simple random sampling. I agree that the Latin hypercute sampling is often the preferred method for the reasons actually mentioned in the text. On the issue of random number generator, the point here is that all computational tools use methods that produce pseudo-random numbers. It's impossible to get perfect random numbers. And I'm not sure if we need to mention that at-risk prefers using EPA I'm not sure if we need to mention what at-risk prefers unless EPA recommends this method. Note that the Mersenne twister method is the default method for almost all professional programming tools, such as Gauss, Maple, MATLAB, or Python, etc. And finally, on this section, E10.3.5, aggregate the simulation results and produce output statistics. Sometime earlier in the Monte Carlo process, the target percentiles of interest should have been specified. In this section, we learned that EPA typically uses 50 percentile and 95 percentile of the output of the central tendency and high-end estimates, respectively. Really, the justification of the target percentile should be specified in a previous step. This last step is simply an operational one. Run the model, collect the results, produce the statistical estimates for the key output parameters. So that's the end of my comments on the Monte Carlo methodology section. Next are the detailed comments on the strengths, uncertainties, and the incorporation of variability. And I thank Dr. Henneman for actually providing the backbone for this discussion. I've just added and modified a couple of his statements to just clarify. So under strengths, we list 4 things. The Monte Carlo approach allows integration of information from multiple sources, and it allows use of summarized, incomplete, or even biased information into one logical framework. It allows propagation of uncertainty in model parameter values through to the pre-identified critical endpoints in statistics. It allows use of monitoring data to validate modeling assumptions and to support the utility of the findings. And it allows integration of a large number of scenarios to increase confidence in those findings. So on the question of uncertainties, this is what we have here are really general comments on uncertainties. I think there's going to be a bunch of specific comments on uncertainties that are going to show up in question 1.b. So assignment of model components, the input parameters, to distributions for a Monte Carlo assessment is dependent on having published values, on analysis of data the EPA has been able to accumulate, or on estimates derived from expert judgment. None of these information sources guarantee accurate and unbiased distributions that reflect model component values across the target population. Some approaches produce better distributions than others, and this is going to be discussed in question 1b. If the population of interest is vaguely defined, the parameter distributions are themselves likely to reflect this uncertainty. Knowing key distributional parameters like the minimum, the mode, and the maximum for a model component typically will not inform the shape of the distribution. Identification of shape, defined by descriptors such as unimodal, skewed, bounded, etc., requires more than 2 or 3 parameters. Some would argue that even having extensive measurement data on a parameter does not guarantee that we know the distributional shape, because measurement data often have limitations imposed by the measurement process. For example, they have a lot of below detection limit observations. Sampling from available data, i.e. bootstrap or jackknife methods, typically require more observations than are available. The uncertainty in shape propagates into uncertainty in the Monte Carlo assessment results. Published distributional parameters, such as the lower bound, the upper bound, and the mode that we see in, for example, table E12, often come without any measure of the uncertainty in these estimates, i.e. without standard error estimates. Depending on the shape of the distributional form assumed for a model component, if the model is sensitive to values of that component, a small change in the distributional parameter variables can actually produce a big change in the distribution of one or more of the key outputs. And of course, this needs to be thought about in the plan for doing a sensitivity analysis. The third property is incorporation of variability. The goal of Monte Carlo modeling is to propagate variability in model inputs through to model key endpoints. The extent to which the exercise is successful depends on getting all of the previous mentioned steps correct. Monte Carlo methodology typically does not do a good job of capturing variability in situations where good measurement data are not available for most model inputs or parameters. True Bayesian approaches, for example, where parameter distributions are created totally from expert insights without any measurement data, have been suggested for use in other risk assessment scenarios, such as in the global warming models, but these approaches typically come with low confidence. And this brings up kind of a last topic that was not alluded to in the question, but came up in some of the comments from Dr. Hinneman and Dr. Ottinger. And that is confidence in Monte Carlo assessment results. And I'm not sure I have these comments right, and I'm hoping to get more comments on this. So in the draft document, the quality of the risk estimates is assumed to be dependent on the quality of the underlying information and data used. How the quality of this underlying information and data is assessed is discussed in section C 4.2.2 and in section E.8. And in section C.4.2.2, specific descriptors are provided for each quality level, for example, high, medium, low, critically deficient, etc. And this is done for various metrics, for example, sampling methodology, analytical methodology, etc. The scoring is then integrated into a weight of evidence assessment. Table E10 provides a summary of the overall weight of evidence for releases based on each OES. What's not clear is how the data quality rating for the modeling component is derived. The monitoring and modeling quality assessment in the draft document seems to be based primarily on the quality of the data rather than on some holistic assessment of the Monte Carlo process. For example, how does the tightness of the distribution of the key output parameters factor into this final rating? A couple of panel members wondered if a more formal quality assessment process might be created and applied to the Monte Carlo modeling exercise. Is it possible to derive a quality label assigned to the Monte Carlo modeling results through applying quality values to model metrics? And finally, we have a set of about 5 or 6 technical points that we're going to include in the final report. These are mostly word changes or areas where particular phrases may need to be re-examined by EPA because they're either unclear or captions have vague, images have vague captions, etc. And I think at this point, I'm going to turn it over to the other discussants for their additional comments. I apologize for the length of this, but there was a lot here that I thought needed to be fixed. So with that, I'm going to move on to the next discussant, which is Dr. Baker.
Hi there. Thank you. I have nothing to add. Appreciate the summary. It was a joy to hear you share.
Dr. Barakal, Veronica.
Yes, hi. First of all, I wanted to apologize for not sending my comments, but I've had quite a bit of personal challenges in these past days. I also saw the summary that you shared, and it was so exhaustive that was really very little to add. I just wanted to add a couple of things. First of all, I think since the comments were initially, that you shared initially went to discuss from the beginning mostly the issues that there were with the Appendix E10, I wanted to say that I think that the choice of the agency to embrace an approach that explicitly accounts for uncertainty and variability is the right approach and a good starting point, given the uncertainty and variability and the limited information that we have on the amount of 1,4-dioxane that is released as a byproduct of industrial and commercial practices. The overall description of the Monte Carlo simulation methods presented in the document can be improved, and Dr. Portier and the other members have provided suggestions on how to reword some of the language used in the Appendix E10. Some comments that I wanted to provide regarding strengths, weaknesses, and incorporation of variability. So as an obvious strength of the approach is it allows to obtain an environmental release assessment of dioxane that attempts to propagate some of the uncertainty and the variability in a coherent fashion based on physical and chemical properties and relationship. A limitation of the method is that it does not account for all sources of uncertainty. The Monte Carlo methods proposed by EPA appears to be focused on addressing uncertainty in the inputs parameters of the model, but it does not question whether the mathematical formulation is correct or there are other possible uncertainties, such as are all the potential sites and mechanism of release included in model? Is the mathematical formulation that links the parameters of the various discharges correct? I also wanted to add to what you said regarding the fact that there is a difference between uncertainty and variability. Although mathematically, they tend to both be represented with distribution, in the case of uncertainty, the distribution is there to represent the stochasticity in a variable and the fact that we do not know the value of a certain variable correctly. In the case of heterogeneity, the distribution showcases the variability in the values of a certain variable in the population. While most of the parameters that are considered in the Monte Carlo method described by the agency in Appendix E, and for which a distribution is used, belong to the first case. That is, we do not know what is the correct value for the parameter that describes a certain physical or chemical key variables, such as, for example, the mass fraction of the dye formulation in the dye bath, in the case of the table E12 in the appendix. In the case of a parameter such as the number of operating days or in the textile production rate, the distribution, in my opinion, does not represent the stochasticity of this variable, but rather represent the heterogeneity in the number of operating days across the different facilities for which we have monitoring data. And right now, it's not clear to me how to interpret the output of the Monte Carlo model. So taking as example the model for a 1,4-dioxane release as a byproduct of textile dye release, it is unclear whether the central tendency output of the model represents what is the estimated 1,4-dioxane release that describes what would be the typical, quote unquote, amount of dioxane release that a typical facility produce on a typical day in a random location, or what is the interpretation of that output? It would be good to have some clarity regarding this. Then I have a comment with respect to the distributional choice. The monitoring data, the TRI and the DMR data can provide some guidance on how to specify the distribution for some of the parameters. For example, in the document, the agency in Appendix E7 has elaborated how in certain situations, the data reported in the TRI is censored to the left because of a threshold, or it might be estimating values too low or too high. This information is extremely valuable and could be used to derive distribution for parameters and not simply take the monitoring data and create a distribution around it. In case where it is expected that the TRI and DMR data provide an underestimate or an overestimate of a parameter, simply using monitoring data to create a distribution or select a distribution based on the characteristic of the variable might be ignoring the fact that the monitoring data is not a simple random sample from the population, but it is actually a preferential sample, with the preferential mechanism being defined by the threshold that exists in the case of Form A, the number of employees, and so forth. So in this case, defining a distribution that addresses the unrepresentativeness of the monitoring data is really important. And then the last thing I wanted to talk about was sensitivity. I agree with you that sensitivity, in my opinion, should be used to look at whether the final distribution of the summary statistics changes substantially when the distribution of the parameters is changed, rather than confirming the results. And then I agree with your discussion regarding the number of simulations.
So,
Thank you.
Your comments?
We have two more. I want to circle around to Dr. Hanneman as well.
Thanks for the comprehensive summary. I have nothing to add.
Thank you.
And Dr. Ottinger.
Thank you. I am in agreement with everything that has been stated and just have a couple of more technical comments to add quickly. There's a large amount of data and variability as discussed in detail. In section 2.2.1.2, lines 1729 to 1815, there's an example of this, and the table in Appendix E8 lists weight of evidence conclusions. According to the lines 17771 to 17776, I might have too many sevens in there. The Monte Carlo modeling is used in tandem with GSs and ESDs, but not for all analyses. And given that the report states this may be a limitation, the table should specify where or if this limitation may affect the weight of evidence conclusions. The only other comment would be the sampling method, lines 7893 to 7900, specifies preference towards the use of Latin hypercube rather than Monte Carlo, with the rationale for efficiency and potential for clustering and underrepresenting low probability events. I agree with that, but I think it would be useful to the reader to add more information here and specify in the report where each is used. Thank you. And thank you, Dr. Portier, for a very encompassing synthesis of everybody's input to you.
So Dr. Cobb, I'm going to turn it back to you to see if anybody else on the panel has
Right.
comments.
Right. Thank you, first team of discussants, Dr. Portier, for pulling all of this together, and each of you for adding your contributions. We now take comments from the rest of the panel, and Dr. Chasen has her hand up. So, Dr. Chasen.
Let's see, just a second. Thank you. And my compliments, Dr. Portier, for all of the great points that you brought up in this. I just wanted to bring up one opportunity about the use and characterization. Just as Dr. Portier suggested, I think it's really important to for the agency to somehow characterize the quality of how they have utilized a tool as powerful as creating distributions by any of these means. And to that point, I'd like to just mention one issue that will be discussed later on when we talk about pests in 3B, but use of creating distributions of sets of data could be very useful for helping to identify a pest situation. Data relevant to unique scenarios for any of these databases, such as those associated with pests, may have a significantly different distribution than those data representing, quote, general populations. So this presents an opportunity to use the Monte Carlo to identify pests based on this kind of a scenario of evaluation of the data. And it's an opportunity to note the quality of the data and the distribution characteristics of each, the general population and each pest. Note that combination of these two data pools without such investigation may alter the characteristics of the generated combined distribution in terms of values at the tails, stabilities of the distribution values at any point, and uncertainty, et cetera, making combined assessments more problematic than they actually would be if those two data sets had been separated. So this, I think, comes up as an issue in terms of quality of the distribution, as well as a unique opportunity for EPA to explore whether or not they indeed do have a pest exposure situation in particular. Thank you.
Thank you for those comments. And please, Dr. Chasen, if you will, send those comments to Dr. Portier so that he can incorporate those into the overall.
I certainly will.
response.
Thank you.
Dr. Apte.
I have a quick question about the Monte Carlo analyses included in this and other parts of the manuscript here. I'm assuming what we see is the end result of these analyses, right? And not so much of the running of the model or any of the data that goes into there. Am I right on this? Or those parts are included somewhere in the appendices? And I wonder if some of that should be documented somewhere, because if an independent, group wants to run them, they might be able to rerun some of these calculations if they find that interesting or would like to do that. So that I just wanted to get some clarification on that. Thank you.
So do the discussants or the agency have a response to that?
This is Franklin.
We've got an echo.
Yes. So this is Franklin Hall. To respond to that question, so yes, the assessment or the risk evaluation contains the results of the simulation runs. It does not contain the pre-aggregated results. I do certainly understand the commenter's point that it would be helpful for folks who want to try to reproduce the results, or at least try to reproduce the results that we present in the risk evaluation, for them to see sort of the intermediate results before the actual model runs that are presented and the output results that are presented in the risk evaluation. So that is something that we certainly could consider going forward.
Thank you.
So this is Ken Portier. I think the point I was trying to make, Dr. Apke, is that showing these intermediate results is part of the model validation process, being able to validate to those looking not just at the end result, but make sure that the intermediate is logical and follows expectation. You know, if the end result looks good and the input looked good, but in the middle it looks screwy, which can happen sometimes, then you have to scratch your head and say, how do I get a cake, but I didn't add eggs? You know, there's something's missing in the formula, and it forces you to go back.
This is Udayan Apte. I would also say that including that somewhere where there is public access to it or access to scientists would just increase the confidence overall on the analyses, right? On the decisions and analysis and everything, just become transparent, and just confidence goes up way high on these things that you're including for sure.
All right, thank you. I see Dr. Ginsburg has his hand raised.
Thank you. So I've run into some probabilistic data in various parts of this supplement, and it wasn't always clear the Monte Carlo methods behind it. For example, in some of like tables G2 and G4, where there's a distribution presented. Earlier today, we talked about the 99th percentile versus the 90th percentile of down the drain releases, et cetera. So there's various inputs to those stream concentrations, dilution factors, stream flow inputs, down the drain releases, consumer uses, sheds, data. There's so many different moving parts to, say, table G2, and there's obviously variability somehow accounted for, but it's not clear. So my thought, and maybe I've missed the boat here, but I didn't see in this document an overall game plan for where Monte Carlo was going to be used to define variability, where sensitivity analysis was going to be used, what was going to be just purely data driven based upon high confidence data. It would have been good to have maybe an overall chart of the different kinds of outputs and which ones were going to be Monte Carlo driven, and if so, then what are the key distributional shapes that were used in defining each of the variable parameters. So that's sort of an overarching comment. I have a specific comment on table E12 with the textile dye, which I didn't spend a lot of time on this, but for example, the mass fraction of 1,4-dioxane in the dye formulation was a single point estimate from the 2020 version of the risk assessment. And I'm sure the model is going to be pretty sensitive to the dioxane. This is sort of the starting point of the whole thing, I would think, is how much dioxane is in the material going into the manufacturing process, and it's just a single point estimate. So I know it's that number comes from the 2020 document, but more than that little paragraph, I think it's 11.6, E11.6, that just says, it comes from someplace else. Would be nice to see what's the quality of that data, how much data went into that single point estimate. Why not, if there's more than one measurement point, why not Monte Carlo it or provide some kind of variability? I'm sure it's a sensitive point. So that's, without doing a deeper dive, those are just some of my comments on the overall use of Monte Carlo.
Thank you. Are there other comments from the committee? Dr. Barakal.
Yeah, I wanted to comment on this need for more information. Sincerely, I found the document to be a huge, a big amount of information to digest, and I understand the need to have more information about what distribution has been used and what is the range and this and that, but I think it's also very hard for the agency to try to do everything at the same time. Like I felt that they provided quite a huge amount of information on the different formulation of the different models that they use, what are the parameters. There is a table that tells you basically whether a value was kept fixed versus a distribution was used, what was the distribution type, what was the lower bound, upper bound, mode. So I think that and this is already at 484 pages, if then there was also added information about this parameter has been kept fixed because of this and that, we would be looking at the document that is 700 pages. So maybe it would be good to have some information streamlined in appendices that are separated from the main document so that people who are interested can go and look into that. But I don't know if it is just me who struggled to go over all these tables and all these equations. That to me, I've reached my limit of the amount of information that I could read in one major draft document. And so I just wanted to say that maybe I would be in favor of having a separate document that goes more into the details of the Monte Carlo methods rather than add additional pages to this particular one.
Thank you. Other comments from the committee? All right, so I think we'll thank the discussants from charge question 1A again, and we can move on to charge question 1B.
Great, thank you. Mary Fox here.
Mary, please wait just a second. I'm sorry. The agency needs to read the record into the.
Oh, yes, right. Sorry.
Read the question in the record, and it's my fault for not stating that.
Well, again, this is Franklin Hall, and I will be reading charge question 1B. For the exposure and release assessments, EPA assigns statistical distributions based on available literature data or standard probability distribution assumptions appropriate for limited data sets to address the variability in several parameters. Please comment on the distribution selection and if EPA should consider any additional parameters for inclusion in the model equations.
All right, thank you. Now our lead discussant is Dr. Fox.
Great. Hi, Mary Fox. So on behalf of the team of discussants here, so we certainly want to recognize the level of effort that the agency put forward to develop the supplement, and including all of the data and distributions built into the exposure and release models. Overall, there's very limited data available, and standard distribution assumptions were frequently used. As I'll describe, the committee does recommend revisiting certain distribution assignments. And also we have comments on some of the assumptions that may contribute to underestimates, and also recommend some sensitivity analysis that may be informative. For the second part of the question, additional parameters for model equations, we did not have anything to add up to this point. So to start with some general comments, first we'd like to note that there's a discussion on the representativeness of the toxic release inventory and the discharge monitoring reports for the occupational exposure scenarios as a whole, and we found this to be a good discussion. I think Dr. Portier mentioned before that in terms of the descriptive general text about the Monte Carlo methods, I mean, it's appropriate but generic. And yes, I would recommend referencing the agency's own past documents on this method. The agency approach meets the standards of fit for purpose using available literature and standard distribution assumptions. With that said, it is notable that uncertainty estimates are not featured in the results. So in this, we're talking about quantitative uncertainty. A limited sensitivity analysis in some cases may provide useful insights. We will provide some references on statistical approaches to account for uncertainties in exposure assessments. Commonly used statistical approaches that are described may guide assessment of uncertainties for the 1,4-dioxane exposure assessments. One major point of concern is the way the surface and drinking water monitoring data were evaluated. The assessment focused on detected values, but that represented only a small fraction, less than 10% of all results. So we're talking about the vast majority being non-detects, and this comes up a couple of times. So more robust analyses should include the values where results were below the limits of detection, and we also provide a reference on that. So the next section that I'll that I've grouped some comments under is additional data or understanding of processes that would indicate a different distribution assignment. For the annual use rate of fracturing fluids containing 1,4-dioxane and the mass fraction of 1,4-dioxane in hydraulic fracturing additive or fluid, these were modeled as discrete with very few values. That does not seem to be adequately representative of an industry where in 2001, according to the Energy Information Administration, there were over 900,000 fracking wells in the United States. So this particular, it may be useful to think about a triangular distribution for this particular parameter. Also for the antifreeze exposure modeling, jobs per day was modeled with a triangular distribution. Discrete may make more sense for this process, as in, there's a discrete number of cars that are serviced per day. And the consumer use rate of antifreeze, so the supplement notes that commercial use rate data were not found. And it appears that only like a top up of antifreeze amount was modeled. But of course, there is the possibility that a full sort of flush and refill of antifreeze is done. And so I recommend that a discrete distribution with greater probability on the small top up amount, but also with some probability of the full replacement be considered. The next group of comments relate to the lack of clarity or need for additional information to assign a distribution, or really to understand the agency's choice of the distribution assignment. First, we have the daily use rate of detergent. The statistics provided for this parameters distribution does not really provide enough information for the reader to understand the distribution used. So the OECD 2011B reference provides tables of statistics of annual use rates, but also lacks sufficient information on how the use rates were modeled. In the container residual fraction of totes, drums, and pails. So The residual fraction distributions are assumed triangular based on lower mode and upper bound estimates. This is attained from the ChemSteer user guide. 4 models are mentioned in the OECD 2019 reference as useful for estimating container residue releases separately from large containers, drums, and small containers and solid transport containers. The US EPA HERO database has no reference for these models. All of these seem to be based on a 1988 study, releases during cleaning of equipment. But this, we couldn't find this one. If this study could be found, could these data suggest a better choice of the distribution form rather than the default triangular? The next relates to the textile release model. Most of the random variable parameters were assigned as triangular distributions here. So most, but not all. And so our comment about this is, you know, you could use a triangular for all of those, but sort of, as has been alluded to before, some additional information on sort of why distributions were assigned in some cases or single values were used in others. Additional information on that would be helpful. Textile production rate. Based on the 1994 EPA scenario document, is itself based on one 1993-94 analysis of data provided in fabric finishing pre-manufacturing notifications. This assessment has no citation, but seems to be a personal communication with sales staff. So again, it's either more explanation here or perhaps identifying a more updated reference would be helpful. Mass fraction of the dye formulation in the dye bath. So there's an OECD 2017 reference here as the source. Again, it's we're concerned that this is may not be adequate to really explain the choices here. There's concern with the accuracy of data on container size for dye formulation. And the references the OECD 2017, which states that dyes can be transported in containers ranging from 25 to 1,000 kilograms. But according to a correspondence with Dr. Warren Jasper, most are shipped in 35-gallon drums. So the sort of a quick search of the web finds some other information for the container size. Typical containers are 30, 32, or 55 gallons, or we have liters here too, 113, 120, or 210. And tote sizes are typically 135 gallons, 275 gallons, or 330 gallons. Dry powder might be shipped in 72-gallon fiber drums. The smallest container was an 8-gallon or 5-gallon. So we feel that the container size needs to be rechecked and potentially updated. We have a couple of figures that I think our friends at Endina may be able to show for us. So can we go to the second slide, please? Great. So this figure corresponds to the comment here. So this is fraction of dye product affixed to textile during the dye process. Different triangular distributions are used depending on the dye type, and this is in table E13. What is reported is the modal value in table Appendix E13 is actually the average fixation percentage default value. which is in table 1-2 of the OECD 2017. When dye class is chosen with equal probability and values simulated using the dye class specified triangular distribution, the final fixation percent distribution looks like the one we have here. So it may suggest a different choice of distribution for or assignment of distribution for that variable. Can we go on to the next figure, please? Okay. So this figure corresponds to the following comment. So this may contribute to additional discussion on the equation Appendix E3. Note that because the mass fraction of 1,4-dioxane in the dye formulation, container size, and dye density are in the denominator of equation Appendix E3, it is very likely the final results could be very sensitive to minor changes in these values. The distribution of the number of containers unloaded per site per year is a random variable, since it depends on random variables, container size, and the daily use rate of dioxane per site day on the random variable textile production rate. Essentially, this is a ratio of two triangle distribution random variables. It does turn out that the variable n container unload site year has a log normal distribution, which we have shown here, and is not particularly sensitive to the fixed parameters. Okay, thank you for sharing the slides. So these notes are on Appendix E13, hydraulic fracturing modeling approach and parameters for estimating environmental releases. So section E.13.12, mass fraction of 1,4-dioxane in hydraulic fracturing additive or fluid. We have a question about what the difference is between the mass fraction of 1,4-dioxane in hydraulic fracturing, fracturing fluid, and the mass fraction of 1,4-dioxane in the hydraulic fracturing additive. The assigned distributional parameters are discussed, but differences between the values are not. So there's some questions about the process here and whether understanding the process may inform a different distribution assignment. There's potential, you discuss potential for correlation between these key parameters, but not why the correlation might be expected. From the text, the resource frac focus 3.0 submissions data set contains data. So a data informed joint distribution might be developed. It is not clear whether the actual Monte Carlo that has been done correlated the values or not. Also, a discrete distribution typically is used for random variables where there are a discrete set of possible values. With the variable F-dioxane fracturing fluid and F-dioxane additive, they're both assigned discrete, but we do not know what those discrete values are. Perhaps it is lower bound mode and upper bound modeled with equal probability, but so that's a question for clarification there. Section E.13.5 on container size. Typical drum sizes for liquids start at 30 gallons. Does the 20-gallon lower bound represent a situation where a partial container is used? Is the variable n container unload year an integer? Can it contain a fraction, suggesting partial container use? What is assumed about the unused fraction of a container? Is it saved or disposed? So again, some additional discussion would be helpful there. Regarding E.13.6, diameter of container opening, most barrels have a standard 5.08 centimeter or 2-inch opening, but is this also true for totes? Again, a quick internet search finds that a tote tank for chemical transport has a larger 6 to 6.5 inch or 6.25 inch threaded fill port and a 2-inch drain valve and a 2-inch male quick connect cam lock. So there's suggestion here that there's different data that could be used for container opening. In section E.13.10, container fill rate, the assumption here seems reasonable. So I won't read that one out. So that one looks good. But we have the details, we'll include the details in our comment. Another set of comments were about cases where a data set is mentioned that could support an empirical modeling approach to the distribution choice. First, related to operating days under textile dye modeling. So operating days here are assumed a triangular distribution. From the OECD 2017 document, we find a search of 31 past pre-manufacturing notice submissions from 2006 to 2014 revealed an approximate average 157 operating days per year over a range of 31 at the 5th percentile to 295, which is the 95th percentile days per year. This suggests that there were at least 31 values for operating days that could be used to determine the form of an underlying distribution. Also, under this, in this case, detergent modeling, also operating days. So the assumed triangular distribution from, again, it's an OECD document, but this is 2011B. There were 600 industrial laundries that provided data on operating days from 1994 to 2002. Again, so that would seem to be a substantial data set that could inform a distribution for that variable. We also have several sensitivity analyses that we would recommend. And two of these relate to, again, we're back to the issue of data sets where there were substantial numbers of non-detect values. So we were concerned about understanding sensitivity of different ways to the ways we model or treat the non-detect values. And we offer a couple of references to support the potential different approaches that might be used. So this relates to line 7519. Easy search load module includes a combination of setting non-detects equal to 0 and or 1/2 the detection limit. So what is the impact we're concerned about? Like, could we model that differently? Could we handle the non-detects in a different way? Let's see. Yeah, so this also relates to, so there's three toxic release inventory range codes. 1 to 10, 11 to 499, and then 500 to 999 pounds. When you look at the TRI data tools, we see a midpoint of each of those ranges. Could we instead assign a uniform distribution to this variable covering the full range as opposed to just the midpoint? This relates to line 7571, where facilities report to TRI with Form A. EPA used the Form A threshold. for total releases of 500 pounds per year for each media release. For example, fugitive air, static air, surface water, POTW, etc. EPA used the entire 500 pound per year for each release media. However, since this threshold is for total site releases, the 500 pound per year are only to one media at a time. So this would, we're concerned that there may be a double counting or overestimating happening here. What is the impact of randomly distributing the total release as fractions to the different release media? There are two situations that may result in underestimation. One relates to line 7528. So the EPCRA section 313 states that facilities may estimate their release quantities using readily available data, including monitoring data that are collected for other purposes. When data are not readily available, EPCRA section 313 states that reasonable estimates may be used, but we would like to know more about whether reasonable estimates correspond to monitored levels of similar sized sites. In the laundry detergent exposure modeling, temperature was modeled as a single value at 298 Kelvin or 25 Celsius. It can certainly get warmer in a commercial or industrial laundry, given the use of hot water and dryers. So I think this would underestimate exposure. But I'm not aware of other data that we could use to support a change here. And then we also had just a few text edit typos, etc. The one substantial one relates to request for some additional text around how we differentiate or describe an industrial laundry versus an institutional laundry. And that's all I have.
Thank you.
Sure. Dr. Cobb, do you want me to call on the associate discussants or do you want to do that?
You are welcome to, but I can do it. I'm not particular either way.
Okay, well, I'll keep talking, I guess. So Dr. Chasen, do you have anything you'd like to add?
No, I appreciate your summary. Thank you, Mary or Dr. Fox.
Great, no problem. Dr. Jajak.
Okay, I'm just coming off mute. No, I thought that was really a good presentation. I think you really went into the details, and I don't have anything to add.
Great. Dr. Portier.
Thank you. I just wanted to take credit or blame for the two image examples. Those are situations where I just got curious as to what the intermediate results look like. I mean, to me, the value of the model kind of depended on whether the number of containers per year was reasonable, and I don't know whether the upper bound of like 5,000 containers per year is reasonable, but I guess if the containers are 30 gallons, I could see them using in a big facility using 5,000 in a year. And then the other thing is I'm always aware when you have a random variable over a random variable, you're likely going to have a screwy statistical distribution of the result. So it's always important to look at those variables because weird things can happen when you do those kinds of things. And so that scenario, luckily, it turned out really nice. It looks very much like a log normal distribution, which most of us would be happy with. So that's the only comment I had. Thank you.
Great. And Dr. Potter.
Dr. Fox, thank you for that excellent presentation. I really appreciate you going deep into the weeds on this and focusing on some critical issues. I don't have anything else to add. I heard the comments that I made. You incorporated them in the presentation very well, and thanks for doing that.
Okay.
So thank you to the discussants. Now to the committee. Are there questions from the rest of the committee, or not questions so much as comments? I guess although questions could be warranted. Any comments? Well, seeing none, we are exactly to the minute. Mary, you did a great job. Dr. Fox, you did a great job getting us exactly to the break point. So now it's time for us to take a 15-minute break, and we will resume at the top of the hour. So thanks, everyone. Okay, welcome back, everyone. Hope you had a good break. We are now moving on to our next charge question, and that will be charge question 1C. And if the agency will read that into the record.
Hello, this is Franklin Hall. I will begin reading charge question 1C. EPA relied on reasonably available information to identify model input parameters. For these parameters, there is uncertainty into whether the input data adequately captures the variability in the true distribution. Please provide additional sources of reasonably available data that may improve the parameter distributions for consideration in the development of distributions.
All right, thank you. So our lead discussant for this topic is Dr. Ottinger. So Dr. Ottinger, please take it away.
Thank you. You can hear me all right, right, George?
Yes, we can hear you fine.
Okay. I'd like to thank the associate discussants, Dr. Verkel, Chazon, Jayok, and Wright. And what I've done is compile the responses from them and my own, along with presenting in sequence their specific comments, because they each provide valuable vantage points for the consideration of EPA. Our goal is to identify additional sources of data to improve the parameter distribution for the development of these distributions. My comments are about the uncertainty and the association of uncertainty with the sources of data, with the most reliable being considered reports of monitoring data. The reports of monitoring data over time provide information about the comparability between sites and change over time. Estimations based on extrapolation from known measures and previous data are necessary and essential to fill in data gaps. And the use of the Monte Carlo methods are really important and appropriate for producing probabilities for effects based on available data. So they're a valuable approach to involve the range of possible outcomes and convergence of effects of influencing variables on outcomes. And much of this has already been discussed previously. Some additional sources of data might include the Monte Carlo simulations utilizing parameters generally with known information and availability. See F.8.2 lines 10678 to 10681 for an example. When data are not available, the use of triangular distribution could be a limitation for the assessment. A more conservative distribution that reduces underestimation would be preferable where possible and based on existing data. A wide range of data sources are already considered, and the EPA is complemented with these efforts. It's an enormous set of data and data sets. There are some caveats that could be considered. Aging and lifestyle are critical parameters to consider as data on effects become available. Should there be a consideration of exposure to mixtures, and how could this be integrated into the models? Then what about nonlinear effects, and how is this incorporated and represented in the models? Is this inherently part of the Monte Carlo method and analytics, or are other methods, more appropriate for this? There is a fundamental issue to be considered in the use of models when data are not available or are older. And models provide a very powerful means of being able to move ahead and utilize the data that are coming from emerging techniques from other frameworks such as exposome, which are developing and projecting adverse outcomes. And all these should help increase the availability of data. It is a challenge to balance the safety and health of individuals and populations with the use of models. And I would recommend moving ahead with the use of models utilizing available data. Dr. Chazone's comments include the following. My comment introduces a different contamination scenario than those considered for the metrics and the modeling. As this is far from my field of expertise, I hope the experts on drilling practices / fracturing can consider this scenario and its importance for estimating contamination and ultimately exposure levels under varying realities, and thus all of the statistical views on the estimates. This practice seems to be relevant for a range of drilling ways, not just fracturing. Hopefully others on the SAC will consider this issue. I'm sure the public would like to know we've considered it. In addition to the statistical considerations, it seems that at least one additional scenario exists, which could influence variability imposed from real-life disposal practices for hydraulic fracturing produced water. Some states permit fracking waste to be spread onto roads to melt ice or suppress dust, references provided. That scenario does not seem to be represented in EPA's calculations, as it is quite different than represented by the surface impoundment analysis using DRAS line 11651. This scenario plausibly could contribute to the variability as well as introduce areas of pool contamination in communities where the practice is common. States that permit spreading on roads for ice and dust control with or without regulations related to contaminants include New York, Massachusetts, Ohio, Pennsylvania, Vermont, Kansas, Texas, from conventional drilling operations as well. Although some testing is required, 1,4-dioxane does not seem to be on list of required testing moieties. And the reference would be from Rebecca Harrington, Scientific American, March 5th. And that would be 2015, and there's a reference provided. Not only fracking waste, but produced water from conventional drilling is also involved. Dr. Jajac's comments include the following. Air released estimates, parens 2.1.1.4, focus on fence line exposures. No mention is made of any other releases during commercial or consumer use products. That is no attention to near field sources indoors that could provide the majority of exposure potential. Instead, we see later in the report that there is a dependence on limited monitoring data. EPA has been a pioneer in modeling inhalation exposure from paint over the last 30 plus years, such as wall paint exposure model, WPEM. The modeling using our best aimed estimates of reasonable worst case for 1,4-dioxane concentration and indoor scenario parameter distributions using Monte Carlo would have provided a much richer assessment that acknowledges and quantifies our uncertainty around this potential exposure and health risk. Defaulting to weak, incomplete monitoring data could falsely conclude the existence of a significantly lower level of exposure than may actually be extant. Using the above modeling approach admits to the relative lack of data and knowledge around this exposure potential. It appropriately trades conservatism for data, which has become or should be a strong touchstone for the RA process. It could also challenge interested and invested stakeholders to provide data to refine the resulting broad exposure distribution to render more confident and typically lower estimate. Refined data could come directly or indirectly from the manufacturers who, if faced with these potentially high estimates born of high uncertainty, could provide more information on residential 1,4-dioxane as an incidental contaminant. They may even have or could implement a production specification setting a maximum level of this compound or total VOC that they could certify from their data and management of our process. This reviewer was particularly taken by public comments by ACC, ACI, and API in that it appear willing and able to provide OES information in collaboration with the EPA assessors. This could allow a generalized modeling approach with the agency providing defaults that would give the manufacturing, selling stakeholders an opportunity and notice to provide confident and reasonably certified OES data. Dr. Wright's comments include, to me, the issue is not so much whether additional data sets can be included, but the proper interpretation of the existing data. Occupational exposure data frequently misrepresents actual exposure. These can be overestimates or underestimates. For example, the plant manager may have asked the technician to determine the worst case exposures in order to select adequate controls. Alternatively, he or she may have wanted to minimize exposure and reports to higher management, the union, workers, compensation carriers, or regulatory agencies. There are many ways to do this without directly falsifying the results. Production can be cut back, ventilation can be increased, workers wearing personal monitoring equipment can be kept in low exposure areas, leaky vessels can be run at lower pressures. Sometimes it's as simple as opening all the windows. This can be done when monitoring is performed by regulatory agencies, and it can afflict environmental monitoring as well. The classic example is increased production at night when opacity monitoring is impossible. Sometimes the highest exposures are completely missed by routine workplace monitoring. Maintenance workers often have the highest short-term exposures, but are monitored less frequently than production workers, and sometimes not at all. The gap between production and maintenance exposure is especially large in the chemical industry, where production often takes place in closed seal reactor vessels. When something fails, maintenance workers are required to open and sometimes enter that equipment. Monitoring those tasks is infrequent. It was not clear to me whether OCS SPP defined maintenance workers as workers or occupational non-users in the RE. Some examples: a Canadian gold mine had a surface plant recovering arsenic trioxide from arsenical mine tailings. The system was fully enclosed, used cold, wet electrochemical methods. Personal and area monitoring under routine conditions showed very low exposure, yet urinary arsenic levels were extraordinarily high. It turned out that the plant was frequently down for maintenance, at which time workers who did both production and maintenance had to enter the reactor's storage vessels with inadequate protective equipment. A second example, in 1992, EPA sponsored a regulatory negotiation to write a new NESHAPS, hazardous pollutant air standard for coke oven emissions. One coke plant stood out with recorded emissions that were a fraction of the industry average. However, the monitoring was done by local air pollution control agency, whose practice was to give the enterprise advance notice. Coke ovens operate under positive pressure for production and to avoid damage, but the pressure can be curtailed for several hours without much impact. And that was done whenever the inspector showed up, greatly reducing leaks from coke, oven doors, and lids. MSHA requires mine operators to operate, this is a third example, to operate coal mine dust with a direct recording personal sampling device worn by one miner per area per shift. The chosen miner is supposed to be the highest exposed, but it's well known that some mine operators move that miner to a lower exposure area or tests on the day they wear equipment. This can happen even when MSHA does the monitoring, since one mine inspector cannot watch all the miners with dust monitors. Even so, monitoring by agency personnel is generally more reliable than monitoring done by employers under a regulatory mandate. Finally, I was involved in a major epidemiological study along with several industry counterparts. It was our job to characterize exposures, to explore a possible dose-response relationship. It proved impossible. Recorded exposures varied widely between plants, and we concluded that without knowing the circumstances under which monitoring was done, we had no way of knowing whether any particular data set was representative. While I think that underestimates are more likely than overestimates, both can certainly occur. This is not a criticism of EPA or any regulatory agency, nor of the majority of employers who are genuinely interested in accurate data. My point is that the data sets should not automatically be taken at face value, and that knowing something about the circumstances under which they were collected can be helpful in their correct interpretation. Now I'd like to add some notes from other SAC members. One set is from the chair, lines 1894 to 1897. These assessments would be much more robust if monitoring data requirements were triggered when EPA initiates a TSCA risk determinations for a chemical or class of chemicals. And then lines 1609 to 1612, there's no reason the manufacturers of dyes, soaps, and detergents cannot provide one for dioxane content of their products. This would allow estimation of air emissions from these sources. Dr. Portier also provided some additional input and asked, are there specific pharmacokinetic and pharmacodynamic models, see Portier responses for charge question 1A, that would provide additional information that could make the distribution more accurate? See also Portier response for adding information in tables, Appendix E12 and E14, appendices, for distinguishing random variables and assigning distributions. Parameters listed in these tables are detailed and inclusive of variables influencing the distributions and models. Further description of random variables could help refine interpretation of outcomes. Finally, the process of inclusion and refinement of the data sources should be as independent and with qualitative assessments that have reduced as much variability as possible. Dr. Portier provides notes from question 1B on Appendix E .11 on textile dye modeling distributional assumptions, that more data might be available from published reports on operating days with assumed triangular distribution. From the OECD, the 2017 document, we find the statement, a search of 31 past PMN submissions from 2006 through 2014 revealed approximate average of 157 operating days per year over a range of 31, fifth percentile, to 295, 95th percentile days per year. And this is from EPA 2015 OECD document, does not provide the reference for this. This suggests there are at least 31 values for operating days and is more than enough to allow determination of whether the triangular distribution is more relevant than, say, the uniform simple quartile data plots would be adequate to justify the underlying distribution. And my apologies if these have already been covered. I have a couple more quick comments from Dr. Portier. Textile production rate based on 1994 EPA scenario document, US EPA 1994, US EPA Hero ID 4286532, which is itself based on one 1993-94 analysis of data provided in fabric finishing PMNs. This assessment has no citation, but seems to be a personal communication with Burson Resin sales stat, September 16th, 1994. Is this really the best estimate? Container residual fraction of totes, drums, and pails. The residual fraction distributions are assumed triangular based on lower mode and upper bound estimates obtained from ChemSteer, User Guide, US EPA 2015A. 4 models are mentioned in OECD 2019 for estimating container residue releases separately from large containers. EPA OPPT bulk transport residual model. Drums, EPA/OPPT drum residual model. Small containers, EPA/OPPT small container residual model. And solid transport containers, bags, fiber barrels. For example, EPA/OPPT solid residuals in transport container models. The US EPA Hero database has no references for these models. All seem to be based on a 1998 study. US EPA 1988 releases during cleaning of equipment, US EPA Hero ID 8731013. If this study could be found, could these data suggest a better choice of a distributional form rather than default triangular? Finally, operating days, assumed triangular distribution from OECD 2011B, discussion just before table 0-2, page 32. There were 600 industrial laundries which provided data on operating days for the years 1994 to 2002. Do these data suggest a distributional form that is significantly different from the triangular? I suspect the distribution will look more like a normal or log normal form. And that's it for our comments. And thank you. Dr. Barakal, you were going to provide, is it all right, Dr. Cobb, if I go on to the discussants?
If you are done and you would like to run through your discussants, that is fine, Dr. Armitage.
Great, thank you. All right, Dr. Barakal, I believe you are going to contribute your comments now.
Yes, I only have one small comment that is going to take a few minutes. So I don't have suggestions of data sources that the agency could leverage to define parameter distributions. My only suggestion regards an approach that the agency could use to construct distribution for parameters. Specifically, in the draft supplement in Appendix E7, the agency discusses different instances and provides reason as for why the values reported in the TRI or DMR database can be interpreted as underestimating or overestimating the actual variable. This information could be used to create a distribution that puts more mass on the lower end, respectively the higher end of the distribution, depending on whether the monitoring data is assumed to be overestimating or underestimating a certain variable. The shape of the distribution could also be adapted to reflect the beliefs of the agency with respect to the representativeness of the monitoring data for the entire population. In other words, what I'm trying to say in here is that if the agency believes that the monitoring data is not representative of the entire population, the histogram of the monitoring data could be adjusted to create a new distribution that would be maybe more representative of the entire population. Within the Bayesian statistical framework, there is a rich literature on elicitation of prior distribution that are based on expert opinion and limited historical data. Even though the agency is not using a full Bayesian modeling strategy to characterize environmental release of dioxane or to characterize exposure to dioxane, the methods for prior elicitation could be used in this context to elicit and specify distribution for some of the input parameters for which limited monitoring data is available in the TRI and DMR database, as well as leveraging the scientific knowledge of the members of the agency that are involved in this effort. And I'm happy to provide some references as for prior elicitations in the Bayesian literature.
Thank you, Dr. Barakal. Dr. Chazon?
Thank you. I have, since I sent the comments to you, I found another reference that I think would be quite valuable for EPA. It appears that the National Cancer Institute, together with Yale School of Public Health, has been monitoring air and water for contaminants, including one for dioxane, for quite some time. And one of their references, there may be others, but this one, it was in Science and the Total Environment. I'll include the details for that reference. It includes the summaries of relevant articles about how the fracking is done, as well as the at least claimed association to these contaminants. So I'll be sending that out for this. There may be other related publications from this same group later on. So if I find those, I'll include those as well. Thank you.
Great, thank you. Dr. Zajac? Can't hear you.
Yeah, that's because I couldn't find the mute button. Okay. Yeah, I thought it was a great summary. I appreciate your integration of everyone's comments, including mine. I did want to add one thing that actually Dr. Cobb and I agree, this is the place where it belongs. He mentioned earlier that I had some comments I wanted to get into the record. So here goes. Basically, the quintessential task of the EPA is to rationally regulate human and environmental exposure to chemicals. Under-regulation results in damage to people and the environment, while over-regulation harms the economy. Both harm the national interest. Parties providing public comments yesterday were sharply divided in their opinion that the 2020 and the supplemental 2023 risk evaluation either over or underestimated the exposure and risk to this chemical. A significant portion of this disagreement comes from their perspective and viewpoint relative to the uncertainty posed by the risk evaluation. Uncertainty born of a lack of knowledge typically dominates the uncertainty of most risk evaluations, including this one. Enhancing the scientific process to render less uncertainty should be a principal point of energy for the agency. And this is my primary point. I advise a primary enhancement of the scientific process by the agency would be a reversal of the current agency paradigm that considers monitoring as superior and preferable to modeling. Monitoring data typically is presented without any contextual information about the primary determinants that cause the exposure. Even if these determinants are representative, the assessor is blind to what factors actually cause the exposure to happen. Models, on the other hand, literally represent the hypotheses for the various exposure scenarios. Example, properly constructed, they provide the explicit, open, and detailed elements of the OES. A good model is the best faith technical representation of the reality that caused the exposure to happen. Properly formulated, it represents the most and hopefully the vast majority of elements that made the exposure happen. All of these model pieces are explicit and available for inspection and analysis. All are ready and able to be described by probability distributions while being completely open to refinement with confident data. Monitoring data with or without contextual information on modeling determinants could perform the function of evaluation and refinement. From the pre-meeting written comments of the commercial stakeholders, they appear to be reasonably motivated to provide data that would render a more confident risk evaluation. Clearly, absent good, solid, more complex information, the agency is properly compelled to trade conservatism for data that will appropriately overestimate the exposure and risk in the initial release of a risk evaluation. Given a reasonable appeal process, the manufacturing stakeholders could identify the sources of uncertainty in the initial assessment models and conduct the work that would provide significantly certified, less uncertain, and more confident inputs. This would invariably lower the putative risk in the evaluation. They could also mandate risk management options such as product specification for the maximum amount of chemical allowable in the products they sell. The end result would be a more rational risk assessment process that does not dramatically overestimate the exposure and risk while providing confident knowledge of actions needed to protect people and the environment. Going back to some of the things that Mike Wright mentioned, the idea would be to verify information from stakeholders. Don't trust, but verify it, and set up a infrastructure to do that. Okay, that's I wanted to get that into the record. Thank you.
I'd like to interject something here. Thank you for that comment. I tend to agree that the regulated community and the trade associations that have presented information and expressed concerns about the uncertainties and the way that the distributions were conducted have every ability to provide data that would, in fact, solve lots of that problem. And so, and the agency has that capability, and that's one way to reduce uncertainty quite a bit. And I've made that point many times, and probably to the point it's not, for me to say it again, is not terribly useful, but I appreciate your perspective. Now back, Dr. Ottinger, back to you and the rest of your team.
Yeah, thank you. And thank you for the additional comments. Dr. Wright.
Okay, there we go. Was having trouble unmuting. First, let me stress that it's Mr. Wright, not Dr. Wright.
Oh,
but that's
sorry.
But I'm flattered. I don't have a lot to add. I have one further kind of example, and that is that in many cases where an occupational hazard has been identified first by a disease in a particular worker, that particular worker has been a maintenance worker. The best example is probably vinyl chloride. And to me, what that really shows is that many of the sampling that's done in the workplace, since it does not always include maintenance workers, often misses the worst exposures. OSHA, unfortunately, is a problem here as well, because many of their specific standards for specific chemicals, the ones that have been promulgated since the agency was created, it essentially say that you do not have to monitor people who are exposed less than 30 days. And many maintenance workers fall into that category. I do want to say that my comments were not meant to really to affect this analysis so much. I think that obviously EPA can't go back and look at the conditions under which each set of data was collected. But I think going forward into future risk evaluations, it would be helpful if EPA did more to really understand the industries that they were looking at. When I teach college classes on industrial hygiene, I tell people, look, your most important tool is not a sampling pump. Your most important tools are your ears, talking to people who understand the process, and your eyes, actually looking at the process. To some degree, EPA's current method of really understanding an industry is kind of like trying to understand a sport by only reading the rules and reading the scores and never looking at a game, let alone talking to people who actually play the sport. So I hope EPA in the future will really spend some time not just analyzing data, but really understanding the circumstances under which it was collected and what its value really is. Thanks.
If I could make one more comment, please, and then I'll turn it back over to you, Dr. Cobb.
Surely.
Going further on what Mr. Wright has just said, what I found fascinating about this particular question is the vantage point that all of us took as discussants. And that was that from my perspective, I was looking forward to what other sources of data might actually refine the not only precision and accuracy, but the ability to understand these processes and where there might be risk and to assess that properly. Whereas others looked at what has been done and how to go into more depth to refine the data that are potentially available or going to be modeled. It's a challenge, and you know, it's a big challenge, and we all recognize that for EPA, and also recognize all the effort and amazingly complex data sets that need to be worked with to produce these outcomes and assessments. And so I think both vantage points need to be incorporated moving forward. But again, compliments to the EPA for what's been accomplished. And with that, I'd like to turn it back over to Dr. Cobb.
Thank you, Dr. Ottinger, and to your entire team for that good summary of comments. Now we turn to the rest of the committee, and anyone that was on the discussants is still welcome to make additional comments if you have them. But Dr. Portier, your hand is up.
Yep. Thank you. So this comment relates to what constitutes reasonably available data or information and what constitutes reasonably representative information, which are two kind of topics we've kind of talked around on this question. In the draft document, it seems that reasonably available information is limited to distributional statistics, such as the mean, the min, the max, the mode, the upper, the lower bound. That these are statistics that are readily extracted from previously published reports. But what about expending effort to find the data on which these statistics are based? And that was kind of the things that Dr. Ottinger pointed out, some of the comments I made. There were situations where the report said, 500 people, data, 500 bits of data were available, but all we get in the report was, the mean, the upper and the lower bound. And so that previous information is lost. Is that reasonably available information? Were even efforts made to find that data? And we don't know that from this report. So that was one question. The other question was, what about greater use of experts? EPA in certain situations uses experts to establish values for certain input parameters for these modeling exercises, especially when the value needed would be considered a constant. So two situations for the textile dye modeling in the draft document were noted. So personal communications with Bursine resin sales staff, September 16, 1994, were used to establish the textile production rate, and that's EPA 1994, and that's that HERO ID 4286532. And in correspondence with Dr. Warren Jasper at NC State University College of Textiles to establish the container size for dye formulation, which references the ETAD 2011 report and Jasper 2011. I think EPA needs to do more to formalize this kind of information gathering, especially for Tier 1 assessments and especially for model parameters that are logically constants that need to be updated. So, clearly the textile production rate from 1994 probably needs to be updated for 2023. Could we have talked to someone about updating that constant? And the same with the container size for dye formulation. I just found it interesting that I couldn't find a company that produced a 35-gallon container. I could only find 30 gallons and 32 gallons and 55 gallons. And that kind of bothered me that, maybe one, that information may not be reasonably representative of the situation, that we needed to talk to more experts. Can a process be developed that would allow query of multiple industry experts in a formal way, kind of like the way the literature is formally examined in the systematic review? The previous SAC spent a lot of time working with EPA over how to do a systematic review of the literature, how to formally do that, and assign values to certain documents and lower values to other documents based on certain characteristics. Well, couldn't the same thing be done about querying industry experts for some of these numbers and then weighting that expert's value according to certain characteristics? I think this is very doable, and it would be a cheap way of updating key model parameters without having to spend money on big measurement exercises or other things. So expert determination seems to be a quick and easy method of filling some critical data needs to better inform the model, as well as insights that could add to the validation of the model intermediate results, such as the number of barrels used per facility per day. I mean, I assume if you ask facility managers, they probably have a pretty good idea of how many containers they used last year. It cost them money. It cost them personnel to do it. They kept track of it. A quick review of the research literature suggests that there are methods available to combine expert judgments into information that informs values and potentially can inform distributions. And so that's my comment, and I'll send that along to the lead consultant.
Thank you. So are there other comments from other committee members? Okay, seeing none, we will move to charge question 1D. And if the agency can read that into the record, then Dr. Henneman is our lead discussant.
Hello, this is Franklin Hall, and I will read charge question 1D. In the 2023 draft supplement, EPA used Monte Carlo modeled releases to estimate general population exposures and risks. For example, the agency used Monte Carlo modeled releases to water, land, and air from hydraulic fracturing as the basis for general population exposure estimates in sections 3.2.2.1.3, 3.2.2.2.2, and 3.2.3.2. Please comment on the strengths and uncertainties of using Monte Carlo modeled releases as the basis for modeling air or water concentrations intended to inform nationally generalizable exposure and risk estimates for general population exposures.
All right.
Yeah, thank you, Dr. Henneman. Sorry, I couldn't find my mute.
That's all right. Can you hear me?
Yes, we can.
Great. Okay. So these represent my own comments along with comments sent to me before the meeting from the associate discussants. Thanks for sending those along. I've tried to bring out points that haven't been raised in other charge questions, but there's potential. I included overlapping information. I have organized these comments into 4 sections: strengths, general questions, weaknesses, and technical points. So strengths that the discussants identified. First, the Monte Carlo approach addresses uncertainty in site-specific emissions or generic facility emissions. The approach increases certainty that the actual modeled release and resulting risk is captured in the output distribution. The approach integrates a lot of disparate information into a logical assessment, allowing EPA to understand the magnitude of exposures to specific populations and to assess who might be at risk. Okay, moving on to general questions. Monte Carlo analyses may be very sensitive to outliers in the data set used to generate the model, given their impact on the geometric standard deviation. Outliers are sometimes discarded from data sets as non-representative, but of course they may represent real exposures, for example, from process upsets and spills. There's interest from the reviewers to learn how the modeling team handled this issue. Next to question, are the distributions capturing stochastic processes or attempting to address uncertainty in each day's emissions? I think this was brought up in question 1A. So what is the purpose of the stochastic parameter inputs? There are questions about the representativeness of the values utilized for the modeling and probable impact on utilizing the generated distribution for assignment of sentinel and potentially exposed or susceptible subpopulations representation at the upper 95th percentile. Emissions, in particular from hydraulic fracturing, are highly episodic and process dependent. And there's a question that wasn't clear to me. How well do the stochastic processes in the Monte Carlo model capture independent and correlated influence from various processes? And I have a citation here for these specific processes, so you might get 100% of the emissions of some chemicals on a single day. And it would be useful to include that information. And I'll provide the citation. In section E.13.3, there are 411 sites reporting 1,4-dioxane emissions, but it wasn't clear what fraction of all hydraulic fracturing operations this is and how completely these 411 sites represent all sites that emit 1,4-dioxane. Section 2.3.2.4.2 notes that the frac focus database contains thousands of wells in the US. Next, sensitivity analyses to input parameters discussed in line 770 through 7783, but it didn't come through how these sensitivity analyses were used for model development or eventual risk determination. Next, weaknesses. While there's greater likelihood that the actual value, the actual risk or emitted release is contained in input and output distributions, the provided release distributions and summary parameters like the median and 95th percentile are themselves uncertain. The use of Monte Carlo modeled releases alone without some form of ground truth makes validating the results of the assessment very difficult. Monte Carlo assessments require a lot of assumptions to be made. Many will take issue with some assumptions, wishing to insert their own, potentially less justified assumptions. And two more technical points. It's somewhat unclear at various points which year's data is used as base regulation. So I have 3 points listed in our comments that we'll put in the summary report. And then in a separate part of the paper, it's unclear whether values reported represent emissions by state or by individual facilities. And that is all the comments from on charge question 1D. So I think now, following how the others have proceeded, I'll call on our associate discussants to see if they have anything to add. So up first, Dr. Baker.
Is Dr. Baker there?
If not, then let's move on to Dr. Chasen.
No, thank you for capturing those comments, and I have nothing to add. Thank you.
Dr. Portier. And I think you're still muted.
You included the comments that I sent you. There's one other thing that kind of came up in the discussion earlier that I think reflects on this. You know, we were asked to comment on the strengths and uncertainties of using Monte Carlo modeled releases as the basis for informing nationally generalized exposures and risk estimates for general population exposures. And it kind of, it means you have to go back and look very carefully at the Monte Carlo and say, what was it that we have simulated here? The distributional assumptions, are they site specific, or they take into account the nationality that we're trying to look at? So, and I don't know the answer to this, but it's this concept of the combination distribution that I talked about earlier. You may have a site that has a certain distribution of what's going on at that site. You know, how much went in to the well and how long the well drilled and everything else, and what product it used that had 1,4-dioxane. But then a different well might use a different product with a slightly different value. So now, has that well to well or company to company difference been incorporated into this Monte Carlo assessment so that the outputs from the Monte Carlo assessment really represent some national, and I won't say mean, I'm going to say some national upper percentile of exposure, because that's really what we're kind of concerned with here is, you know, do these releases globally, you know, is that been captured in the Monte Carlo model? And I'm going to try to write something and send that to you, Dr. Hammond, but I think you get the idea of what I'm trying to get at here. It's matching this need to do inferences on a national level with whether the specifics of the model address the national exposure or release profile.
Thanks for that. And I sort of agree at various points in the report. I had a trouble, and part of this was because of the screening approach used for the air emissions, that at times they were using sort of national summary statistics, and at times it was more facility specific, and finding a way for that to come through from this 500-page report, I think would be helpful. Doctor, let's go through all the discussants first, I guess, and then we'll come back. It was Mr. Wright, I believe.
Yes. Yeah, I really have nothing to add. Thank you.
Okay, then I guess since Dr. Chasen is on the discussants and you have your hand up, go ahead.
I said I have no comments, but Dr. Potier opened up a topic that I'd like to explore just a little bit more. I am happy and very pleased that EPA is developing procedures for use of modeling, both to assess the information that they have and also to make predictions or try to provide some kind of perspective about the need for additional information and all of the other kinds of things that we talked about. I do hope that the agency doesn't get too bureaucratic about exactly what they do with such distributions. For example, I know it's important to look at uncertainty and variability on that, but it's also important to look at the contribution of any sets of information that are combined to see whether indeed you have unique distributions within those contributing data sets. So if you have, for example, two sets of data, each creating a very different and not necessarily even overlapping sets of values, you can create a very nice looking parametric distribution that looks good, so to speak, when actually you had two unique distributions contributing to it. Dr. Portier, I'm getting dangerously close to your expertise here, so chime in if I get any of this wrong. But that is the value of having these kind of Monte Carlo tools at your disposal, where you don't have to run 100,000 iterations. You can run 100, in a few seconds and see whether you have unique distributions, whether there are sets of information that don't look like the rest of them, and then ask the question, why? What's just as you suggested, Dr. Hanneman, is there something unique about the products that go into here? Is there something unique about the type of landfill that's been contributing leachate? I mean, what is it that makes this? I think we have several illustrations. For example, it occurred to me that in cases where you had 95% of the data set representing values less than the level of quantification or level of detection, I can't remember. You ended up with a distribution using 5% of the data. It was like, oops, well, what is so different about those conditions or circumstances that created detectable values versus 95%? I mean, there should be some learning available from those. And Dr. Portier may have some attitude about whether you can create a distribution and then pick the 95th percentile from 5% of the data set. This is not an uncommon occurrence. EPA has, I know in pesticides office, faces this issue frequently. And so I just wanted to sort of put those editorial comments in to encourage EPA to continue to use it with a very open mind and not get bogged down in underutilize, if you will, but also to take lessons to make sure that they don't get trapped into believing the distributions beyond what the data permit. So thank you.
I kind of wanted to follow up on what Dr. Chasson said, and it just struck me as something. And I think it's the idea that you run a number of Monte Carlo models on discrete scenarios that represent different kinds of fracking situations in that case, or laundry situations in another case. Is the national picture made up as a mixture of different scenarios that represent the totality of the industry, or do we integrate into the distributions of the one model to represent the whole population? And that's a question I don't know, but I get the feeling EPA wants to run the one whole model, and yet a lot of experts, a lot of people who look at the industry, and especially when we start talking about pests and susceptible subpopulations, we start talking about specific scenarios that are part of the whole picture, but maybe driving the highest risk. And so I don't, that's kind of the gist of my comment, is that when you start trying to talk about nationally generalizable exposure and risk estimates for general population exposures, you've got this conflict between trying to look at one model or trying to look at the industry, breaking it up into scenarios, and then using the model to look at the different scenarios, and then qualitatively bringing that back in at the end. Dr. Chasson, I think that's what you were kind of trying to get at.
Indeed. I think that there's not first of all, I think EPA's mission, this is just an editorial comment, is certainly beyond just looking at nationally general population. They seem to have forgotten that there are unique communities for which this kind of calculation certainly must exist by law. Now, however, no matter what there may be process to process, as you suggested, Dr. Portier, or some other factor that we haven't even conjured up yet. And I certainly don't know very much about drilling. So the experts on this panel might be able to list other scenarios where they would expect to see different distributions of contaminant levels. But the point being that the objective here needs to be defined by EPA. What is their responsibility, and how will they use data, which we already know is insufficient to, unto its own, stand up and represent a national perspective. So you're taking, by necessity, pieces of information here and pieces of information there. And so at least at these early stages of use of the Monte Carlo, I would recommend that every pile, if you will, that looks like it might be unique, be examined all by itself, so that the agency isn't sort of fooled into thinking they have some kind of general national distribution, when indeed they have disparate sets of scenarios that are being just mathematically bunched together. And I think that's really an important point, especially early on, till this becomes a more robust, supported and understood method tool. Thank you.
All right, thank you. And Dr. Henneman, is that that's all of your discussants, correct?
Correct. The only thing I'd ask Dr. Chazen, if you could sort of summarize that comment. I tried to take notes, but send it in your words would be best. Thanks.
See, that's the punishment of making a comment. So I'll do that. Thank you.
Thank you.
All right, so now on to other members of the panel. I see there are 3 hands up, and Dr. Barakal was first.
Yes, this is Dr. Barakal. I actually wanted to continue this conversation because it links to something I was thinking when I was working on question 1A. And when I said about the difference between distribution that represents uncertainty versus distribution that represents heterogeneity. And I think it's my impression that, as has been discussed here, that right now we're trying to have a distribution that compounds both aspects of uncertainty and heterogeneity when we are looking at some of these variables that are related to the facilities and the releases. And as a result, I think what happens is that now we have a distribution that is much wider, and that when it gets integrated within the Monte Carlo method, you then get a distribution of exposure that is much broader, which I think will lead to these percentiles being more extremes than maybe they would be if the analysis was done more in a local fashion. And we didn't discuss the SHADS HT model. I'm not very familiar with the SHADS HT, but I have worked with the SHADS PM model. And in that situation, for example, there was, again, a Monte Carlo method approach that was used, but the input distribution were very localized. And the input distribution in that case was the air pollution distribution, concentration of different pollutants. And so in some ways, I think that it could be done here with parameters that are more site-specific and more local, in the same way as I think Dr. Portier was trying to get at when he was discussing the difference between within sites and between sites variation when we describe the distribution of certain input parameters. And so I just wanted to basically add my 2 cents and support the comment made by, oh, I'm blanking on her name, Dr. Chesson.
Okay, thank you. Mr. Wright.
Yeah, I'd also like to comment for a second on the issue raised by Dr. Chason and Dr. Portier. The end of this process eventually will be an EPA rule, and that EPA rule will focus in part on control technology. And for that reason, it's useful to understand what pieces of an operation or an industry represent the greatest risk. So, having individual modeling of those different operations is, I think, more useful in that sense anyway than having one big model of the whole situation. So I would argue for not combining all of this data into one big distribution that rules them all.
All right, thank you. It seems like that's kind of a consensus that, I don't know if it's consensus, at least majority view there, or at least that the agency should consider that. All right, Dr. McKenzie.
So I was just going to further support those statements made by the previous speakers and Dr. Chason. And in regards to hydraulic fracturing, there is quite a bit of variability in operations around the country. This is regulated, the regulation of air emissions and equipment and controls is all regulated at the state level for the most part. Around hydraulic fracturing, it varies quite a bit by what phase of development you are, and the size of the sites varies. There can be 40 wells on a site, there could be 1 well on a site. So there's a lot of variability in this. There's a lot of variability in the controls used, and there's a lot of variability in how produced water, which is one of the things that's been brought up as a potential exposure pathway, is handled on the sites. So I would also say that specific scenarios need to be considered and modeled rather than lumping them all into one total scenario.
Okay, thank you. Dr. Portier is back again.
Yeah, I just wanted to follow up on Mike Wright's comment. EPA tends to tier its assessments. And I think it would be reasonable for them to say at tier 1, we're going to use this global model. We're going to throw in distributions on these parameters that try to represent the totality of the industry, run it through the model, get some upper estimates and get some idea of releases, translates that into overall risk. Then as a second tier, they're going to go back and decompose the industry into these scenarios and run the model on the individual scenarios to be able to understand which scenarios need, management controls and which they can leave alone. So, this does, one of the questions was the benefits of using the Monte Carlo approach. And it can be used at tier 1 as a global tool and at tier 2 as a scenario tool to help you target in on where management needs to be. And so I don't think it's an either or. I mean, it is an and in this scenario.
Okay. Yeah, thank you. Dr. Graham.
Hello, Cynthia Graham. And I just want to commend Dr. Portier and Dr. Chasen for bringing that up. That was a concern of mine about using this for a nationally generalizable exposure and risk, when in fact it's, these are site specific and there are different populations. So will it actually dilute the risk by using it as a national exposure risk? So I just want to commend and agree with what was brought up, and I think EPA should take all of that under consideration. Thank you.
Thank you. I actually have one follow-up to Dr. McKenzie's comment about the variation in hydraulic fracturing operations. I do know that here in Texas, or at least it is my understanding, that it's difficult to get access to sites to figure out what is going on. So if you want to figure out an air emission or a groundwater contamination issue, it's very difficult to gain access. And so gathering that kind of information is extremely difficult, at least in the state of Texas. I do not know about other states, and I don't know if there's anybody that's interested in following up on that comment, but that's one of the things that is a challenge here, at least in our state. So Dr. McKenzie.
And Lisa McKenzie. So I would agree with that comment. It's challenging in many states. There is currently a study going on. There's not data from this study yet that's being sponsored by the Health Effects Institute that is gathering data on what particular processes on oil and gas sites in Texas and Colorado are more likely to contribute to air pollutants. They're not looking specifically at 1,4-dioxane. They're looking mainly at hydrocarbons and VTEX, but that data will likely be available in about another year or two. They're also building a model where you could start to model what the emissions would be from the sites.
Thank you. Dr. Chase.
Yes, thank you, Dr. McKenzie. I was hoping to draw Dr. McKenzie and Dr. Clark into this conversation since I know virtually nothing about drilling. And however, just reading the work that was available online, it wasn't clear to me if EPA knew that the fracturing method was somehow uniquely different from other drilling exercises, and even the titles of some of the research kind of blurs this. It talks more generically. Could Dr. McKenzie or Dr. Clark just make a comment about whether there's some unique difference between sort of the fracking industry and the produced water versus drilling for oil and gas in more conventional ways? On that, that's just a general point of confusion for me, and why EPA just looked at the one drilling scenario.
Thank you. And I see now we have Ms. Jenkins, who is actually our regulatory expert in the state of Texas, who's going to maybe speak to some of this.
Great.
I don't have a lot of information. We have another regulatory agency in Texas called the Railroad Commission that regulates waste from oil and gas drilling activities. But what the TCEQ has done is we have an extensive air monitoring network, probably the largest of any state. And so we have a large air monitoring network in the Dallas-Fort Worth area that was still collecting data, recently published a paper on 12 years worth of air monitoring data in that area. We also have air monitors in other areas of the state that we, in our toxicology division, continually evaluate, and all of that information is on our website. We have real-time monitors that are in place around the state of Texas to look at those types of concerns. So there's one bit of information. And then, yeah, unfortunately in Texas, or fortunately, it's the oil and gas industry is regulated by another state agency.
Okay, thank you. And it'd be important for the agency to know what data is available there, perhaps to send those web links. And I don't know if the agency has that information already in this assessment. I haven't delved so deeply into the nuance there. Dr. McKenzie has another comment.
Lisa McKenzie. So I was just responding to in the oil and gas industry and hydraulic fracturing. So hydraulic fracturing is a particular process used where they use a lot of basically water with some chemical additives in it. And it's used to mostly right now go into some of the more inaccessible plays to release the gas or oil from the resource. It's been used to lesser extents in conventional development in the past, but it's really with the development of the unconventional resources, such as the shale plays, where it's really become very widely used across the US, to my understanding. And also, to my understanding, this is one of the predominant ways of developing oil and gas now in our country. It's predominantly being, new sites are predominantly developed using hydraulic fracturing. And it's a process that actually follows the drilling of the well. So it's part of the development. It's usually not used during the actual drilling of the well. It follows. Thank you.
Okay, thank you. So it looks like we may have gotten through all the comments for charge question 1D. Just real quick, circle back. Are there any other comments? So we're a little bit ahead of time. I want to go to the agency now, the EPA, and see if the comments that have been made are clear, or if there are any clarifications that you would like from the committee about what these comments are.
Dr. Cobb, this is Franklin Hall. I don't have any clarifying questions. I certainly appreciate the comprehensive nature of the comments that I've heard so far through the first set of charge questions. I appreciate the detail that the discussions have gone into with respect to different parameters and certain emission scenario documents that need some revision based on their review. So I don't have any clarifying questions at this point.
Okay. Hey, I do have a question for you, and it's directly related to Ms. Jenkins' comments from TCEQ. Do you know whether that monitoring data that she referred to was part of this assessment or not?
I don't know that offhand, but that's something that I can follow up on, though.
Correct. And I'm not sure the dioxane parameters are part of that, but at least it's a good source of information if you don't already have it in there.
No, I agree with that.
Okay. So thank you very much for that. And thanks to the entire committee and the entire EPA staff for getting through this. Well, it's this morning for me, whatever time it is for the rest of you folks. We're at a lunch break now. We're a couple of minutes early, but I don't think we're early enough to delve into another charge question. I do want to mention a couple of housekeeping issues. There are a couple of committee members who have had some family health situations emerge that make some of Friday problematic for them. So I would like to have our lunch break today only be 45 minutes, and then perhaps our 15-minute lunch break this afternoon be only 10, so that we can try to get through question 2.1b today, as well as 2.1a. So that's kind of warning to everybody about lunch and break schedules, and also to give fair warning to Dr. Prisbilla that it is my hope that we will be to your question this afternoon rather than tomorrow. And if that poses problems for you, just let me know and we'll try to rearrange a different way. Dr. Apti.
So you think that we might get to questions 4 by tomorrow afternoon sometime? You're muted, Josh.
Sorry, that means we would be starting questions. We would be in questions 3 probably tomorrow afternoon. I doubt we'll get to 4 tomorrow afternoon, okay, but it is possible. It is, right. That is always possible.
I just want to be ready, that's all. Thank you.
I appreciate the desire to be ready. Okay, so it's 20 minutes after. So if we can come back at 5 minutes after the next hour, so in 45 minutes for lunch, and we'll pick up there with charge question. I forgot where we were. Charge question 1E. And so with that, thank you everyone, and we'll see you in 45 minutes. All right, welcome back from a somewhat shortened lunch break. I need to take a quick roll call, and then we can proceed with the rest of the afternoon. So, Dr. Apti.
Present.
Dr. Baker. Dr. Baker. Okay. My computer's changing screens on me. Bear with me. Dr. Chasen.
Present.
All right. Dr. Ike. Ike.
I'm here, present.
Dr. Fox.
Here.
Dr. Graham.
Here.
Dr. Hyger-Bernays.
Here.
Dr. Jenkins. Allison Jenkins there? Okay. Dr. Merced Nieves?
Here.
Dr. Messerling cannot join. Dr. Ottinger.
Here.
Dr. Prisbilla.
Present.
All right. Dr. Reif. Dr. Reif. Dr. Rumpler. Dr. Voorhees. Chuck there. Mr. Wright.
Here.
Thank you, Dr. Bennett,
I am here.
Dr. Barakal,
Here.
Dr. Clark,
Here.
Dr. Ginsburg,
I'm here.
Dr. Henneman, Dr. Henneman, Dr. Jajot,
I'm here.
Dr. McKenzie, Dr. Maglino,
I'm here.
Dr. Portier,
Here.
Dr. Potter.
I'm here.
All right, I have several I need to go back to just to make sure we're all here or not right now. So Dr. Baker, Ms. Jenkins,
I'm here.
good. Dr. Rubin,
I am here.
Dr. Rumpler, Dr. Voorhees, Dr. Henneman, Dr. McKenzie. All right, we have several members missing, but we still have quorum, so we will proceed. And if some of the EPA staff can help me look and see if some of these folks join this afternoon, so we'll have the roll correct. All right, let us proceed into our next charge question, and that's going to be charge question 1E. And if the agency or EPA will read the charge question into the record. Do we have an agency person to read this?
Sorry about that. Dr. Cobb, can you hear me now?
Pretty well. It's a little bit faint, but I've got pretty good ears.
Okay, all right. Good afternoon. This is Franklin Hall, and I will be reading charge question 1E. Please comment on the application of the Monte Carlo method taken by EPA in the 1,4-dioxane 2023 draft supplement. Sections 2.1.1 and 3.1.1 are general overviews of the assessment approaches. Appendix E9 is an overview of Monte Carlo methods as applied specifically to this risk evaluation and will be applied generally to subsequent risk evaluations. Appendix F4 includes occupational exposure scenarios where Monte Carlo methods were used to develop distributions for certain 1,4-dioxane occupational exposure scenarios.
All right, thank you. And our lead discussant for this charge question is Dr. Jajot.
Thank you, George. Everybody you can hear me okay?
Yes.
Good. Okay, so section 2.1.1, EPA assess environmental releases, air, water, and land, and occupational exposures, inhalation, and dermal to 1,4-dioxane for each of the OESs listed in table APXD1. EPA used the environmental release estimates for each OES for subsequent environmental concentrations and general population exposure calculations. Table APXD1 represents a complete listing of all OES evaluated. From the perspective of this reviewer, this listing appears to be well constructed and exhaustive. I also agree that inhalation and dermal exposure will compose the majority of potential exposure to this compound in the occupational setting. Air release estimates, section 2.1.1.4, focused on fence line exposure. It struck me that there's no mention made of any other releases during commercial or consumer use of the products. That is, there is no attention to near field sources indoors that could provide the majority of exposure potential. Instead, we later see in the report that there was a dependence on limited monitoring data to estimate this exposure potential, which I'll comment on later. Section 3.1.1, using the 50th percentile as a central tendency and 90th percentile and 99th percentile as high-end estimates seems appropriate. One cannot, however, comment on the applicability of Monte Carlo methods taken by the EPA when the agency did not use Monte Carlo for some critical near-field human exposure scenarios, such as sources to estimate the occupational inhalation exposure. Instead, limited personal sample monitoring data was used for the textile dye, surface cleaner, soap dish, paint, and floor lacquer. Monitoring data was also used for PET byproduct and ethylation process byproduct OESs. If modeling had been used as the primary tool, then Monte Carlo applied to the independent variables of the model would have been possible, and the monitoring data could have been better put into perspective. The agency did use Monte Carlo for human health exposure assessment for antifreeze, laundry detergent, and hydraulic fracturing OESs. The MC approach in all of these OESs appears to be valid. For antifreeze, the AP 42 loading model and the EPA mass balance inhalation model were used with variations in the input parameters. I found this to be a credible approach, especially since it appears that there is relatively low exposure risk from this analysis that can be confidently predicted from this source. On the other hand, if the results had turned out to be high, it is suggested that the source rate from the EPA model be used to run the near field far field model from IH-MOD, and I provide a reference for that. Similarly, approaches for industrial laundries is fine, and it is credible and also renders a relatively low exposure risk estimates. Again, I think the point here is that when you have relatively low estimates, you don't have to have the sharpest tools in the deck. The model results from hydraulic fracturing really stand out. They present perhaps the overall highest inhalation exposures in the evaluation. Clearly, these modeling results beg for a more detailed analysis by a modeler with experience in near field, far field model that has Monte Carlo capabilities, and that as is the case with the AIHA model suite, AIH-MOD. Expert opinion, as advocated by Mr. Wright, along with possible follow-up on-site visits by regulators to perform monitoring, is also indicated. The report addressed Monte Carlo modeling of environmental concentrations for far field releases in the various OESs. For my brief inspections of them and their rationale, they appear to be fine, but in previous discussions, they may not be. I leave it to other co-discussants more knowledgeable in this matter to comment further. It appears as if Monte Carlo was not formally used to estimate the central tendency and upper end for absorbed dermal dose. However, the MC could have been applied to variables of the dermal absorption exposure model that was used. For example, currently the central tendency and high end for the model variables S, Q sub U, and Y sub derm are put in as single deterministic values for CT and HI. These variables could be described and used in the Monte Carlo simulation as distributions along with other variables used to determine the 50th and 95th percentile of the model determined dermal exposure. Appendix E10, developing models that use MC methods. We are advised that this appendix is only intended to provide general knowledge or general background information related to the specific MC models. Given the above intention, my sense is that this section should have some further discussion defining terms. The word stochastic used in this document needs some further perspective and definition. The definition in the Merriam-Webster's Collegiate Dictionary for stochastic is that it has Greek origins, meaning skillful at aiming or to guess at. To aim at or guess at. When we have good data defining the natural variability around a variable, that, for example, adult male body weight, this distribution is not stochastic. It is a well-known probabilistic distribution. we are not guessing or aiming at what we think the answer is. We have good data and essentially know the answer as a distributional portrayal of reality. When we have poor data and apply our best judgment to assign a variable, and perhaps only only have it perhaps a broad range with or without an estimated central tendency, the distribution is significantly more stochastic than known. All MC distributions are probabilistic. Most of them are a mixture of variability and lack of knowledge. When the lack of knowledge is dominant, they are weakly known and strongly stochastic. So I think these concepts should be basically teased out and defined in this section. Somewhere in this section, the advantages of this important tool should be put forward. Specifically, Monte Carlo analysis can, by using sensitivity analysis, show which variable is or are driving the exposure. If the distribution is wide because of lack of knowledge, then further investigation can pay big dividends in providing confident knowledge to narrow the distribution. Monte Carlo shows the degree or width of uncertainty and possible exposure, and if mostly from stochastic variables, our lack of information and confidence in the distribution. And Monte Carlo allows for sharing this analysis, the details of this analysis with risk managers, and thus it basically includes them in the process and makes them part of it. Okay. So I provide some references for the previous comments. Dr. Fox questioned whether the need value of Monte Carlo modeling is adequately explained in the document. In the section developing models that use Monte Carlo methods, E10, the general description is appropriate but generic. It would be helpful to see the agency's own guidance and relevant scientific literature cited in support of the approach. Two things seem to be missing in describing how distributions are assigned selected. One, an understanding of the context, the industrial activity, products, and process being modeled can also be helpful in assigning distributions. Two, when there are some data available, a statistical analysis will fit an appropriate distribution as possible. She comments that this is an empirical approach to identifying distributions. She also agrees with the use of Latin hypercube sampling to ensure the full range of values is drawn from when the model is run. Okay, comments on Appendix F4. As mentioned above, the inhalation exposure assessment for textile dye is just uses monitoring data that is typically highly skewed with a few very high values and mostly lower values. Trying to explicate this difference and exposure situation with modeling rather than simply using these monitoring data represents a lost opportunity. This represents a significant number of highly exposed people, but undersampled folks in this industry. Similar comments are also provided above and developed below for other OESs. In an effort to strengthen the scientific approach, I am making the general recommendation to default to the use of MC modeling as the first and dominant approach, with available monitoring as support, as a support piece. I made those comments previous, but I will discuss this specifically for the situation with paint and flour lacquer as a general case to be applied to all OES that simply rely on limited monitoring. Again, we see that monitoring data was used for paint and floor lacquer worker exposure estimates from one NIOSH on-site study in 1989. The assumption is that one site and the limited number of paint formulations used there are representative of all sites and all paints. There's no information provided that indicates the concentration of 1,4-dioxane in these paints. Clearly, the universe of paint formulations used in the US is potentially much broader relative to their potential bulk concentrations of 1,4-dioxane. Also, there's no details on the specific exposure scenarios at the site, which may be better or worse elsewhere. All this begs for a broadening of the analysis via MC Monte Carlo modeling, fed with the best estimates or even professional guesses of reasonable worst case input variables. Dr. Ottinger further developed this recommendation in her previous comments. And that's all I had.
All right, thank you. So now going to the associate discussants. Dr. Baker, do you have any further comments? Is Dr. Baker here? Dr. Fox?
Nothing to add.
Thank you. Dr. Henneman?
No, nothing to add. Thanks.
And Dr. Portier?
I just have a question. I thought EPA wanted comments on the try to CDR crosswalk, which I didn't hear in Dr. J. Jock's discussion. He discussed E10, and I thought it was for E9, because the whole idea of the question was the exposure data, looking at exposures. I don't have anything to add here. I just wondered about that. Dr. J. Jock, did I read something wrong here?
I thought they had I thought they labeled E10 incorrectly as E9, so I just simply read it as E10 and commented on E10.
Maybe George, you might want to ask EPA.
Yeah, I was just that was my that was going to be the next things out of my mouth was clarification from EPA if it should have been E10 instead of E9 or.
I mean, I looked at E9. I didn't see anything to comment on. I mean, it made a lot of sense. It's a big section. Is
there anybody there from EPA?
Yes, sorry about that, Dr. Cobb. Yes, so that is correct. It should have been E10, not E9.
Okay.
Okay. So, Dr. J. Jock, you are a mind reader. So, yeah, and maybe if we can correct that for the record, that would be great. All right, so I think we've gotten through all of the discussants. Are there other comments from the remainder of the committee? All right, if not, we can move on to charge question 1F, and if Dr. Hall, you can read that into the record for us. I think you're muted again.
All right. Thank you, Dr. Cobb. We're bringing the question up now. This is Franklin Hall. I will be reading charge question 1F. Please provide feedback on any scientific considerations that EPA should contemplate when considering Monte Carlo methods in release and occupational assessments for future risk evaluations under TSCA.
Thank you. And for this, we have some of the same folks we've been hearing from with a couple of new additions. And Dr. Barakal is the lead discussant for this. Turn it over to you.
Yes, thank you. This is Dr. Barakal, and I'm going to read a comment that incorporates the comments I have received by some of the associate discussants, not all of them. So the problem of characterizing release and occupational assessment is a complex one, given the heterogeneity, uncertainty, and limitation of monitoring and exposure data. The complexity and the number of physical and chemical processes that lead to dioxane as byproducts and its release in water, land, and air, as well as the different routes of exposure pathways. While this is true for 1,4-dioxane, we believe that this consideration extends to other chemicals under TSCA evaluation. Because of the complexities in the sources and types of chemical release, life cycle in the environment, proximity, and other factors affecting exposure, and the limited amount of definitive, almost error-free data on both release and exposure, using a Monte Carlo method approach to represent and evaluate release and occupational assessment and account for uncertainty and heterogeneity in the input parameters and key factors is appropriate, and at least in my own opinion, a scientifically and statistically defensible approach. Dr. Oettinger also justifies and supports the use of Monte Carlo methods because this is a quote from Dr. Oettinger: they allow to add a level of complexity that is difficult to incorporate into traditional deterministic calculations and models, such as, for example, secondary metabolites, effects of sunlight, interactions of complex mixtures. With a push to develop methods that capture exposure in a more encompassing way, Monte Carlo methods provide flexibility in approaching and gaining a better understanding of the scope needed for assessing specific chemicals. Actually, this was not a complete exact quote. I have moved some words around, but basically these were Dr. Oettinger's words. Dr. Potter also supports the use of Monte Carlo methods for future task evaluation and has provided a list of useful links available on the EPA website that can provide guidance on the use of Monte Carlo methods in risk assessment. And there is a list of at least 5 websites that I'm not going to read here during this public comment, but will be incorporated in the report. Some of the documents are somewhat dated, more than 25 years, and might need updating. For example, the 1997 document that summarized policies for use of multivariate methods in risk assessments. The process can guide the use of Monte Carlo method under task evaluation when exposure assessments are linked to probabilistic determinations of risk. So at least for the 3 of us who are all in support of the use of Monte Carlo methods for future task evaluation. As for what recommendations to keep in mind in future implementation of the Monte Carlo methodology, we have already discussed on some of the recommendations while answering previous charge questions. And I will recall some of these recommendations below. First, it is fundamental that the agency, in cooperation with other agencies and other entities, associations, professional societies, works in increasing and modernizing the amount of data available on both the release and the exposure front. While this will not solve the data need issue, at least it will limit the likelihood that the measure of central tendency and high-end estimates of release and exposure assessment are unrealistic due to outdated data. Besides an improvement of the data front, another important consideration for future implementation is the choice of distribution used to represent uncertainty and heterogeneity. The suggestion here would be to choose and specify distribution that leverage both the information in the data that is available, but also address the limitation in the data, whether it is censoring, lack of representativeness, and so forth, by combining the information in the data with input and opinions from experts, both within and outside the agency. So this is to go back at the comment that I had made regarding the elicitation of distribution that follows the prior distribution elicitation that is used in Bayesian statistics methodology. As release and exposure assessment models will become more complex, it is recommended that the agency seeks and provide scientific justification as for the choices used in the Monte Carlo method implementation, clearly stating and explaining why certain input parameters are kept fixed and constant and why others are provided with a distribution. The agency should also work on validating the results obtained from the implementation of the Monte Carlo methods to ensure that the model formulation, parameter choices, etc., lead to valid and plausible values. Given the likelihood of increasingly more complex model formulation, it is also important that the Monte Carlo methods are implemented using a large enough number of simulations that leads to an output distribution that is well represented. Maybe in future task evaluations, besides addressing uncertainty in the input parameters and heterogeneity in the inputs, future implementation of Monte Carlo methods could address also uncertainty in the deterministic model formulations, perhaps considering different functional forms that link the various input parameters, and apply a Monte Carlo method approach also with respect to that aspect. That would entail, for example, that each iteration not only a value for the input parameters from a specified distribution is sampled, but also there is a random sampling of the functional expression of the deterministic model to use, thus accounting also for this additional source of uncertainty. And finally, I will conclude with a recommendation suggestion by Dr. Potter that involves the use of artificial intelligence, AI, in risk assessments. His recommendation is that the agency works on formulating and establishing policies and procedures that regulate the use of AI in task evaluation and other risk-based assessment. With the field rapidly evolving, AI is expected to play a significant role in risk assessment in the future. I think this name is pronounced Whittower, but I'm not 100% sure. Whittower et al. 2020 provide a concise description of AI use in chemical risk assessment. A recent application of machine learning to predict 1,4-dioxane concentration in groundwater on Long Island, New York is also insightful, and it illustrates the potential of AI and machine learning technique. And this is there is another citation to De Simone 2023. So that's all I have.
Right.
And
Thank you. And so we have additional discussants. Dr. Barakal, do you want to run through those discussants? Or do you want me to do that?
If I find the agenda and the names, I can do it. Okay, so the associate discussant for this question include Michael Jajok. Dr. Jajok, do you have anything to add?
No, nothing that, other than what I've already been mentioned in on this subject.
Okay, thank you. Dr. Ottinger.
Thank you. You did a wonderful job capturing everything, and I really appreciate it. One small question, which is actually reiterating something I mentioned earlier, was the sampling methods, lines 7893 to 7900. It goes back to the use of Latin Hypercute rather than Monte Carlo.
Sorry, I didn't read that because I didn't understand whether it was part of the answer to this question or not. But
yeah, no.
If you want to mention it.
Yeah, no, the only reason to mention it is because of the rationale for choosing one over the other. And the comment in the report was that the Monte Carlo would have less efficiency and potential for clustering and underrepresenting low probability events. And so I just wanted, a little more information about that, especially if the tendency is to use primarily Latin Hypercute. And that's all. Thank you very much.
Thank you. And then Dr. Potter.
Thank you, Dr. Barakal. You certainly covered the question thoroughly and highlighted comments that I submitted to you prior to the meeting. One thing that I've been sitting back here listening, and a lot of dialogue about what guidance we might give the agency on this. And one thing that I would like to see, and I say this in part because I'm not a specialist in Monte Carlo methodology, is having the agency put together some form of case study where the principles and practices can be laid out for lay persons like myself to comprehend and perhaps gain a deeper insight into where the agency's headed with this. I think there seems to be some communication issues that need to be worked on, and perhaps that would be one path forward.
Okay, thank you so much. And Dr. Rumpler. Is Dr. Rumpler online?
He was not here earlier this afternoon, so perhaps he is not present.
Okay, so I guess how we'll proceed then.
Yeah, so that's all of the discussants. I would like to say one thing just quickly related to the comments I heard is especially for Dr. Ottinger's comments, there are very likely to be places where there's redundant response in the charge questions, and we should figure out where the best placement of that response is, and then refer back to that response in other charge questions. And we will do that in review of the documents as they're being with the document as it is being crafted. And so that's among the discussants, but also I'll add myself to make sure we get that right. Okay, other discussants for question other committee members for question 1F. Any comments? Oh, Dr. Portier, your yellow hand is against something on your background that has a yellow tint to it, and I didn't see it. I apologize.
Thank you. So, sometimes we kind of miss the obvious on some of these things. And to me, a Monte Carlo assessment really should be no different than any other data analysis, which is what we're talking about here. It's much more complicated, much more comprehensive, but it's a data analysis. And with that frame of mind, the related key scientific considerations that I look for in considering these Monte Carlo methods is, one, to make sure other researchers, risk assessors, have all the information needed to replicate the Monte Carlo assessment. Replication is a key determinant of a scientific endeavor. If you can't replicate it, it's not science, it's voodoo or something. So you have to identify all the assumptions or the conjectures that you're making, state them clearly, show all the data available to support or justify your assumptions, including these expert inputs that I talked about before. Justify assignment of model parameters as constants, justify assignment of model parameters as random variables, justify setting model parameters that should vary to be constant, clearly describe, not just label, the statistical distributions assigned to the random parameters. And then the second thing is you need to discuss any data that supports or disagrees with the Monte Carlo analysis finding, what we call assess model fit. We haven't spent a lot of time talking about model fit, but you need to assess both the final results and the intermediate products. That is the statistical distributions of the derived random variables. And then we need to include in the model fit assessment a logically based sensitivity analysis. And so I'll send these along to Dr. Borikal to kind of add at the bottom, but it's like a step back in this 30,000 foot view, but sometimes we forget these basic things.
Yes, thank you. I actually have one comment, and it's a very broad-based comment, and it repeats the call for data to actually inform these distributions that are being placed into the Monte Carlo analysis. And I'm simply going to introduce a document from the American Chemical Society on chemical risk assessment and regulatory decision making. I've forwarded this to our DFO, and Ala can place that into the record. I was involved in writing the predecessor to the one that is currently in existence. The one that's in existence today is good from 2023 to 2026. These things are reviewed every 3 years. But principle number 2 in this statement says evaluations of chemical risks should be based on robust, reproducible science and risk-based criteria protective of both human and environmental health. And so to Dr. Portier's comment about reproducibility, that's there, but also that you have robust data to support your assessment. Furthermore, there's some language later that talks about exposure assessments needing robust exposure data, and that biomonitoring is an important aspect of risk assessment. So this is the largest professional science society in the world speaking to this topic. And I think the agency should really do what they can to garner this data and do so in partnership with the regulated community, which also has a responsibility here to provide data that's going to inform these risk assessments. So I see Allah has come on the screen. Maybe he has something he would like to say.
I was just asking you if you want us to show the document or just the cover page of this document.
If you would like, you can. I don't know that it's necessary, but if you think that will help, especially the public, I am happy to do that. And if I can share my screen, I can do that perhaps from here.
Sure. Either way, Will, would you prefer that you show the document or Dr. Cobb can share his screen?
Dr. Cobb is able to share his screen if he wants to do that. That works.
All right.
Let me make sure I got the right one because there's two of them. Where's the new one? I may have just closed the.
Well, Will has it. I sent it to him. If you want to show it, Will, can you?
Yeah, let me pull it up here. Or
I've got it now.
Okay.
I've got it now.
Okay.
That works.
Okay.
Here it comes. Can you see this?
Yes.
So this is the American Chemical Society document, Chemical Risk Assessment and Regulatory Decision Making. And I'm just scrolling down. These are the portions that I was highlighting and speaking to here, as well as here. And there are links that we can put in the public record, as well as the PDF will also be there. Is that okay, Allah?
Thank you. Thank you.
Okay, let me stop sharing. Right. So I was not trying to hijack that conversation, but we got that document into the public record on some previous dockets, and then it's actually just gotten revised in the last few months. So it's probably good to get that back into the thought process. All right, now let's see if I can find where we are. We are now at charge question 2.1 with Dr. Ginsberg as the lead discussant. But you know what, before we go to charge question 2, are there any points that the agency would like clarification on as far as the comments that we have made on through question 1?
Thank you, Dr. Cobb. No, I don't have any need for clarification on any of the points that we've heard from charge question 1. Thank you.
Okay, great. Thank you for letting us know that. And now we will move to charge question 2. And if the agency will read that into the EPA will read that into the record, Dr. Ginsberg will start the discussion.
Hi, this is Brian Groza, and I'm going to read charge question 2.1.a. As described in Appendix G.2.1, EPA used the NHD Plus version 2.1 flow line data for receiving water body flows, including the use of modeled annual and monthly average flows from this database, as well as geospatial techniques used to assign facilities and intakes to reaches when necessary. Please comment on the strengths and uncertainties of applying this data set.
Okay, so I guess I will summarize the comments that I've received in writing, and we'll then.
So first of all, Dr. Ginsberg, just to clarify, this is you speaking.
Yeah. Oh, yeah. I'm sorry, Gary Ginsberg. So I'll summarize the written comments. I'll just read them. They're not that long. So NHD plus 2.1 is a highly robust modeling representation of river and stream flows and geometry across the US. A quick literature search shows that it has been used to simulate water quality in drainage or catchment areas as influenced by runoff, land uses, agricultural best management practices, etc. The draft approach presented in the 1,4-dioxane supplement of simulating point source discharges from industries as fixed locations within the NHD plus 2.1 modeling framework appears to be a new application, but if there are other examples, these should be cited by EPA. NHD plus version 2.1 at a resolution of 1 to 100,000 and containing 2.7 million discrete flow line features is surpassed by NHD plus HR, or high resolution, which is at a resolution of 1 to 24,000 scale and goes from 2.7 million flow line features to 27 million. So a question that we have is, how does EPA expect that using this more robust HR, or high resolution data set, would change the analysis? Was it considered for use in this supplement? Use of NHD plus 2.1 data for estimating flows in facility-specific modeling involved using lowest monthly average data over a 30-year period of data collection. This lowest monthly average was simulated as the 30Q5, which, for those who aren't familiar with that, that's the lowest flow rate over 30 days over a 5-year period. And that seems conservative for contaminant dilution modeling. However, the data are from 1971 to 2000. And so the question is the current and future impact of climate change captured in these data? The harmonic mean flow was also used in facility impact modeling, which is less conservative. However, given that the main dioxane concern is chronic exposure and cancer risk, the long-term average water concentration, rather than the peaks and valleys, is of most import for that analysis. And so the harmonic mean flow as a central tendency, excuse me, I have to get rid of a pop-up. And so the harmonic mean flow as a central tendency and the lowest monthly flow for a 30-year period as the 30Q5 as an upper bound concentration, these are probably reasonable, with the caveat that climate change may be influencing these values. Given data limitations, it may be difficult to involve the NHD plus 2.1 framework into a more dynamic or probabilistic approach. One limitation is using monthly flow averages rather than a distribution of monthly flows. Rather than only 12 inputs per year, it would be ideal to have a range of flows for each month. This could be a distribution based on monthly averages with attention towards climate change scenarios. For example, moderate or extreme drought scenarios when the same release may be less diluted. In California, for example, 2 out of 3 years are drier than the average, so the wet years drive the means. Odds are likely that when a discharge happens, it's going to be in a lower flow year in California. Including a range in scenarios would address this limitation. And I think, let me just keep scrolling. Yeah, that's all we have from the written comments. So if you'd like, I can go through our associate discussants and see if they have anything else to add. Dr. Cobb?
That would be great. Go ahead.
Okay. Let me start with Rainbow Ruben?
Hi, Rainbow Rubin here. Thank you for your summary. Nothing to add at this time.
Thanks, Rainbow. Charles Voorhees? Not sure if he's on the line.
I think he hasn't checked in today, or at least not this afternoon. So
Okay. Mark Rumpler? Again, not responding.
No, I don't. He might not be here either.
Okay. And Thomas Potter?
Okay, I'm here. And thank you, Dr. Ginsburg. I think you've highlighted the value and the utility of the database. I believe it's state of the art. We're not going to get much better than this in being able to represent flows across the continental U.S. And so thank you for your summary. I think you have hit all the most important points.
Thanks, team. Dr. Cobb, I'll turn it over to you. I'll just say in summary, I think the 3 points that we raised here that may be worth checking with EPA on are number one, are there any citations or examples of using NHD plus 2.1 in this type of application for discrete discharge points within these flow lines and dilution from there? Number two, has EPA considered using the HR version? And number three, how is EPA viewing climate impacts on this, somewhat dated data set now?
Yeah, thank you. And I agree with all of those points, but especially that last point with the droughts that we have and the placement of these particular major release points within the U.S. that tends to make me think that probably low flow conditions are lower than are being modeled. So that's, right. Of course, high flows may be higher than modeled, but we're really concerned about the low flows here for the risk assessment. So thanks to the discussants. Now we'll open it up to the remainder of the committee for additional comments. No additional comments. So with that, I think we'll move to question 2.1b. If the agency will read that into the record, then Dr. Przybilla will be our lead discussant for that portion.
This is Brian Groza. I'm going to read charge question 2.1.b. As described in Appendix G.2.1, EPA, in the absence of data, relied on assumptions for specific release amounts and locations. For example, for facilities reporting releases via Form A, EPA assumed 500 pounds per year of releases. For facilities without reach codes in NPDES permits, EPA used the nearest NHD plus flow line within 2 kilometers as the receiving water body. EPA compared the impact on the overall analysis when facilities requiring these assumptions were included, figure 5.1 in section 5.2.2.1, or excluded, figure 5.2 in section 5.2.2.1. Please comment on the strengths and uncertainties of these assumptions.
All right, thank you for reading that in. And Dr. Przybilla, would you like to provide the response?
Yes, Jennifer Przybilla, lead discussant. And how I organize this is first I will read the assumption and any strength and limitation and recommendation associated with that assumption. So for the first assumption, which is for facilities reporting releases via Form A, EPA assumed 50 pounds per year of releases.
for facilities with REACH codes and NPDES permits. EPA used the nearest NHD plus flow line within 2 kilometers as the receiving water body. Strengths identified were given the uneven nature of data on water concentrations of dioxane. Using data from relatively near sources seems reasonable. Despite uncertainties with this approach, it is difficult to see how else it could be done any other way, given how sparse data is on this. Therefore, EPA's approximations are reasonable until such a time as better data can be obtained, and the approach appears to have an appropriate level of conservatism. The computed overall releases will be somewhat higher than the actual value. Table 2.6 shows that using Form A doesn't affect that many facilities, 23% of the 120 modeled, and it's a conservative assumption to use the max in this category. Also, Table 2.6 shows that 67 out of the 120 modeled facilities have a REACH code and another 18 are within 2 kilometers of a stream flow line. So this doesn't seem like a big uncertainty. Limitations. A core question is, how did EPA choose the 120 discharging companies to simulate in the first place? What is the universe and how did they narrow to this subset? There remains questions about industrial water releases estimates from TRI and discharge monitoring reports. Do these estimates line up? Which are more reliable? TRI are self-reported with EPA spot checking. How reliable are these estimates? Recommendations. As needed, a sensitivity analysis could be conducted to evaluate the magnitude of the impact of this assumption. It is likely to be small. The data summarized in figures 5.1 and 5.2 reflect this. The distributions of lifetime cancer risks across all facilities that had releases versus only those with high quality data releases exhibit very similar trends. Using NHD plus HR, which is 10 times more granular, might suggest a different flow path. It would also be better to stimulate these concentrations on receiving bodies that have drinking water intakes. The next assumption, when a facility 11058 assigned REACH code is missing in the ECHO database, the nearest neighboring NHD flow line and 11059 associated REACH code within a 2 kilometer radius was identified using GIS software. This process was repeated 11060 for the facilities reported as receiving indirect releases. A strength identified. This analysis was needed so that 1,4-dioxane concentrations could be estimated when stream data was not available. In this case, definitive hydrologic data was used, and the discussant puts a reference here of a website that I will include in the report. Uncertainties are not specified. However, it is reasonable to assume that flow data provides a realistic approximation to actual values. A limitation is EPA provides limited evidence that this assumption is true. Recommendations, a sensitivity analysis could be conducted where EPA could compare facilities that are within a 2 kilometer radius that do have an ECHO code to prove that assumptions hold true. The next assumption, these model flows are based on an observed flow from the years 1971 to 2000. The mean 11064 annual and mean monthly model QE flows were extracted from the NHD plus version 2.1 database for 11065, the identified reaches. And a strength is that this data comes from a well-established database. A limitations is that the current observed flows could be different than the years 1971 to 2000. A recommendation would be that this time frame could be the only data available. If so, EPA should justify the use of this time frame and why past flows would be expected to be similar to current situations. The next assumption, when multiple 11068 segments were with the same REACH code were returning during the process, the mean of each flow 1109 metric was calculated and applied to the associated facility. A limitation is the inherent limitations of taking an average is that it masks very high or very low flows that can be hidden in the average. Recommendation, EPA should show examples of data to ensure reviewers that high or low flows won't be lost in average
or describe EPA's plan to deal with average problems. And the final assumption is that in 2 instances, the water body associated with 11070 with a releasing facility was a lake or coastal water body without flow metric. In these cases, the 11071 facility flow was used if available. For facilities with no available hydraulic or 11072 facility flow rates, the lowest non-zero flow within the COU was used. And the strength is that using the lowest non-zero flow within the COU is the most conservative approach. And that is all I have.
Thank you. We have several discussants, associates, and I guess Dr. Ginsburg is the next one. First one.
Hi again. Yeah, I think my comments are adequately captured, but I would just add, since I submitted my comments, that looking at the examples from North Carolina that I put onto the chat yesterday and read into the record, I think that there's another type of emission besides POTWs. It's actually related to POTWs, which are not modeled in the current framework. So we're mostly dealing with TRI and other disposal reports. But there is the issue, I think, coming out of POTWs of processed waters from industries that are releasing to public sewer systems that end up coming with some pretty high numbers. If you look at the North Carolina data coming through POTWs, which would not be down the drain type of releases, I don't think, but it certainly needs to be looked at. So I guess I would just frame it as, how well, it gets at that question of these 120, OES related sources for release. How well does that really capture the universe of releasers for 1,4-dioxane, some of which may be going into POTWs and may be their processed water that's being released? How well do we understand that?
Okay.
Thank you.
Dr. Potter.
Okay, I'd like to thank Dr. Prisbilla for synthesizing the comments that I submitted into the discussion. I really have nothing else to add. I'll simply say that I'm a strong supporter of the use of the hydrologic data that's we've been discussing. I think it's definitive and represents something that's important as a close partnership between multiple government agencies, in this case USGS and EPA, and I always see that it being a positive.
Thank you. So have Dr. Rumpler or Voorhees joined us this afternoon? I don't see them in the list. Just want to make sure we're not omitting someone.
I know Dr. Henneman was here shortly after you called his name in the afternoon.
Right, and he made a comment, so I know he was here for a while.
Okay.
So that wraps up the discussants. Are there other committee members who have comments on question 2.1b? Okay, if not, we'll go to question 2.
Sorry, Dr. Cobb, I have a clarifying. Should Dr. Ginsburg send me his additional comments, or Dr. Ginsburg, do you feel like those were adequately captured yesterday?
I can write something up.
Okay, thank you.
Thank you. Now we'll go to question 2.2. That will be led by Dr. Hager-Bernays, and if one of the EPA scientists will read the charge question into the record.
This is Brian Groza, and I'm going to read charge question 2.2.A. EPA applied novel approaches to estimate down the drain releases of 1,4-dioxane in consumer and commercial products as described in Appendix G2.3. Please comment on the strengths and uncertainties of the novel estimation methods and validation of the down the drain modeling in the case studies presented in Appendix G2.3.2. In addition, please comment on the application of SHEDS HT to develop per capita down the drain loading, which may be applicable for other chemicals with relevant product and usage data within SHEDS HT. Finally, please comment on how SHEDS HT outputs are incorporated into the novel down the drain modeling approaches applied in this assessment.
Thank you very much. And then Dr. Hyger-Bernays is our lead discussant.
Right.
And please
Okay.
provide your comment.
Thank you, Wendy Hyger-Bernays. So to evaluate the anticipated ranges of down the drain contributions of 1,4-dioxane to water bodies receiving POTW effluent, a range of combinations of hydrologic flows and populations served by a POTW were evaluated. And then we go on to, for this modeling exercises, only contributions from the down the drain component were used to calculate resulting surface water contributions. Hypothetical combinations of hydrologic flows and populations contributing to wastewater loading, as we heard before, derived from the national distribution of hydrologic flows and population places were selected. Inclusion of down the drain pathways in the 1,4-dioxane assessment is important, and EPA has applied novel methods to estimate 1,4-dioxane in consumer and commercial products. Water concentrations of 1,4-dioxane resulting from down the drain releases depend on the population size, an indicator of the number of people using products and contributing to the releases, as will be pointed out later, and the stream flows of the receiving water bodies. The representative per capita down the drain loading developed from the modeling results from the stochastic human exposure and dose simulation. High throughput SHEDS AT was applied to a range of population sizes, 100 to 1 million people, and stream flows 300 to 30,000 cubic feet per second to develop a distribution of potential surface water concentrations for dish soap, dishwashing detergent, and laundry detergent. Although the approach may be appropriate for the proposed use, there are several concerns and suggestions. A major assumption of the model is that the national average proportion of the population in occupations resulting in commercial use of the consumer products is the same regardless of location. As was raised yesterday, this is unlikely to be realistic, as specific local industries would vary and the population working at those industries would likely be related to the actual local population and provided, for example, NTSB notes the typical commute in 2017 was less than 10 miles. Summary data is for any purpose. However, raw data could be used to estimate actual work commute. The citation is noted here. Similarly, USCB notes typical commute time is 27.6 minutes, which indicates relatively short distances. While utilizing the national average could minimize or maximize facility representation in some locations and skew results, it will increase uncertainty. It is recognized, however, that it may not be possible nor desirable, as pointed out by one respondent with regard to pests. With the information available to revise this portion of the assessment, there is information available to revise this portion of the assessment with this issue in mind. There are several comments from respondents regarding the input parameters, specifically the starting concentrations of 1,4-dioxane. In several places in the text, EPA states that it is not known how much 1,4-dioxane is present in detergent and dish soap. However, there are measurement reports of 1,4-dioxane in such products, and citation is noted, which could have been used in a probabilistic forward modeling approach. In fact, it appears as though starting concentrations may not be reflective of the current marketplace, especially for dish soap and surface cleaners. It is also noted that this concern was raised in the 2020 risk assessment by HCPA/ACI and were not addressed. As noted in these prior comments and comments in the docket, New York has a 1,4-dioxane limit of 2 ppm for 2022 and 1 ppm for 2023 for cleaning products that became effective in 2022. If companies cannot meet the limit, they must apply for a waiver, and the waivers are publicly available at this website. Do I have to read this website into the docket, or is this okay?
No, you don't have to read it.
Okay.
It's going to be presented in the report. That will be fine.
Okay, thank you. Because the starting concentrations may not represent the measured concentrations per capita down the drain loadings for dish soap and surface cleaner appear to be overestimated from the SHEDS HT modeling. Some specific comments pertain to inputs, table Appendix G2 per capita. DTD loading appears to greatly overrepresent dish soap and surface cleaner, and non-commercial dish soap represents 88.9% of all down the drain estimates from SHEDS HT modeling. And commercial down the drain loading dish soap represents 35% and surface cleaner 63%, or combined for 98% of down the drain estimates from SHEDS HT modeling. Now, there are other examples, which I will get to also, which perhaps demonstrate an underestimate. While SHEDS HT has been used by the agency in the context of air exposures, the version used in this risk assessment is unavailable to the public, and the prior version, 0.18, released in 2019 with updates in 2021, is noted as being in the beta version. Therefore, it is not possible for the respondents here to review the specifics. With regard to specifics of this matter, on page 376, EPA states that 1,4-dioxane has been measured from 0.03 to 204 parts per billion in dish soap. The respondent questions the source of these measurements and how they were used in SHEDS, illustrating the lack of transparency with the application of this model. Appendix section G2.3.4 states that product weight fractions generated during the engineering phase of this risk evaluation were used as inputs to the modeling. For laundry detergent, the mass fraction of 1,4-dioxane in product is the upper end of the range from the 2020 TSCA assessment, 14 parts per million, Appendix Table E14. However, two reviewers point out that the mass fraction for dish soap and the documentation of 1,4-dioxane content of products of consumer or commercial nature is not presented in the document. There is no indication whether cleaning products available in the supermarkets are any different in 1,4-dioxane content than the industrial commercial cleaners. SHEDS HT appears appropriate to estimate per capita down the drain loading and has been validated for similar uses as part of its development. However, the way the SHEDS HT loadings were used are not clearly explained. Assumptions are not well supported, and there appear to be inconsistencies in approach between the case studies and the probabilistic model. One respondent states that given the physicochemical characteristics of 1,4-dioxane, additional processes, for example, sorption, could be included in the down the drain model, but were excluded. This is appropriate for conservative modeling and reduces uncertainty associated with higher degrees of quote unquote realism, especially in national scale assessments. For the validation case studies, the mean down the drain loading is used for non-commercial releases, whereas the 90th percentile is used for commercial releases. The choice of the 90th percentile appears to be made to accommodate the expected higher loadings from commercial releases as compared to non-commercial releases. However, neither the use of the median nor the use of the 90th percentile is justified, either qualitatively or via comparison to actual loading rates in the 2022 risk assessment. Although such a comparison may not be possible, ground truthing the results or a subset of the results is a necessary component and would greatly improve confidence in the estimates of down the drain loading for both commercial and non-commercial releases. Moreover, the estimated commercial loadings, this is from table Appendix G2, are manyfold greater than the non-commercial from the appendix, 600 times greater for laundry detergent to nearly 27,000 times greater for surface cleaner, indicating the potential for high variability in the down the drain modeling results. And again, comparing the estimates to measured values would greatly improve the reader's confidence in the EPA's use of SHEDS HT. Section 2.1.1.2 states that for industrial commercial releases not having TRI or DMR data, SHEDS was used to estimate down the drain releases. However, this is based upon total population contributing to a POTW in that area and the percent of the population doing the job. For example, the dishwasher leading to the down the drain releases. EPA used an upper bound 99th percentile consumer down the drain estimate for SHEDS HT for industrial releases. From Appendix Table G4 for dish soap or surface cleaner, the 99th percentile is only approximately 10-fold greater than the mean consumer down the drain release. That is to say that a professional dishwasher in a restaurant working an 8-hour shift and using a commercial dishwasher is only going to put 10 times more 1,4-dioxane down the drain than a typical household's daily load of dishes. The respondent notes this is a questionable assumption and it appears to conflict with Appendix Table G2, which shows per capita dish soap attribution to down the drain releases with the assumption for commercial being the 90th percentile of the consumer distribution, not the 99th, and rather than 10-fold greater than the mean. Table G2 shows 1,000 times greater down the drain releases than the average consumer. Thus, tables G2 and G4 don't seem to align well for the example. The down the drain commercial estimates one gets for dish soap from G2 is 100 times more than from table G4. It is unclear where these various estimates come from. Assumptions used in SHEDS, modeling, and resulting commercial DTD releases should be checked, perhaps by comparing residential versus commercial dishwasher loading, soap uses, run cycles, hours per day, etc., according to manufacturer specifications for the equipment. The last major assumption in the down the drain commercial SHEDS approach is that the 90th percentiles is multiplied by the fraction of the population feeding into any given POTW that work as dishwashers or maids, etc. According to Appendix Table G5, this is one dishwasher job per 93,000 people. When this multiplier is used, it is likely that the commercial dishwashing contribution to overall population release would be minimal, although this breakdown is not presented. Perhaps there are alternative ways to ground truth these product usages, such as what the total amount of dishwashing soap products sold per capita. While the one DTD case study, that's Liverpool, Ohio, does suggest that EPA is underestimating down the drain releases, there are substantial limitations in the validation exercise, which raise further questions about the strength of evidence for this release amount. Down the drain modeling case study is for Liverpool, Ohio, in which a public water supply intake is affected by upstream starting concentrations, an industrial facility, the BASF Corporation, and by the surrounding population DTD releases. However, there's no location identified for the POTWs into the Ohio River, and we don't know what percentage of the population DTD releases would be feeding into the Ohio River via POTW, and what percentage would be on septic and not making it to the river. Another limitation is that there were no detections of 1,4-dioxane at the Liverpool, Ohio intake out of 4 AWQ, out of the 4 water quality sampling result years. And so the modeled concentrations is without a quantified value for comparison. While this appears to be an overestimate, this case doesn't prove that down the drain releases via POTWs wouldn't have made a contribution had there been enough information on where the POTW releases exist and the population they served. Related questions: do the DTD estimates in Table 2.9 contain both the consumer and industry community releases? Down the drain releases do not model contribution to groundwater, yet there are many homes, schools, and businesses that release to septic systems with related environmental releases to groundwater. These releases may affect private wells. It is not clear why the paint COU is excluded from commercial releases. Appendix F identifies that 1,4-dioxane is present intentionally or not in paints and floor lacquer, automotive unfinishing coatings, architectural paints and coatings, and industrial coatings. However, only automotive refinishing coatings are evaluated in Appendix E and are presumed to not be disposed of down the drain. The loading is set to 0 grams per day per capita. It is not clear why these other COUs were not analyzed, or if they were, why they were not presented in the 2022 risk analysis. Further, SHEDS HT appears to predict mean and standard deviations DTD loadings for non-commercial use. However, no percentiles are shown. It is not clear why these would be the case, nor how a mean could be calculated without any percentiles data. Regarding inconsistency, several were noted in Appendix G2. These inconsistencies decrease clarity in the model and input parameters and reduce certainty in the quality of the results. Specific comments regarding these inconsistencies follow. The SHEDS HT model uses, quote, default model parameters and product mass ratios, also referred to as product weight fractions. In Appendix G2.3.1, it is stated that the product mass fraction mass ratios are described in Appendix E. However, in Appendix G, explains that product weight fractions were derived during the engineering phase of the evaluation and no information is provided. Because the term product mass ratio appears nowhere else in the evaluation and product weight fractions only appear in the executive summary, section 1.1.1 in reference to hydraulic fracturing, and appendix or F.4.1.1 hydraulic fracturing, is not clear to the reviewer what values were used in SHEDS HT estimations. Regarding Appendix E does not clarify this matter, as the only references to SHEDS HT in Appendix F are to explain which COUs are modeled using SHEDS HT. Appendix G.2.3.1 explains that the down the drain loadings are derived from the median 90th percentile HT estimates. The results are shown and were presumed to be used in the validation case studies. However, inspection of the case study worksheet shows that although non-commercial DTD loadings were used, commercial releases were considerably different loadings. And so the strengths is that EPA is using a model that has been used for other purposes to account for down the drain loadings data here that does not appear to be available elsewhere. The limitations are that the estimates of input concentrations need to be reviewed and revised based on existing data sources and internal ground truthing with regard to non-typical household use. The lack of transparency with regard to the inputs used in the SHEDS HT model and correction of the differences identified within the document are also a limitation. Thank you. Okay.
Thank you. So we have other discussants. Dr. Harker-Bernays, did you want to go through those discussants, or did you want me to run through them?
I can do that. I'll start with the discussants who had provided the comments. I'll start with Dr. Bennett.
Yeah, good afternoon. Thank you. Yeah, I think my biggest question around here, we talked about the starting conditions and, if you look at, the per capita loading of the differing conditions of use, both the consumer side and the commercial, I would expect those to be similar, at least of the same magnitude or, very similar magnitude. And in many cases, they're off by, a couple orders of magnitude, if not larger. And that, when you finally backtrack to the starting concentrations where the dish soap is so much higher than the other similar products, the laundry detergents, and particular dishwashing detergent, that's where I definitely have that question pops up. I think a couple of had that similar concern. And I could not really extract where they're coming from, and that was a particular challenge. I think in general, I think it's pretty clear that once this is diluted, I think that part of our the challenge you run into in each of these is the down the drain sources are so much smaller than the POTW sources. And I think going back to some of the earlier comments of possibly modeling these separately and then combining the different models to come up with different better modeled estimates might be helpful. I think that was all I had. One other piece that hasn't popped up too, I just I thought of this going through this. It's probably an agency question, is certainly in the consumer space and to some extent coming into the commercial space, there would be non-TSCA uses. I'm thinking shampoos, body washes, etc., that may have 1,4-dioxane. Would they, I would expect those to be contributors at some level. I still expect those to be, very small, but, is that somehow accounted for, or is that even accounted for in the course of these analyses? So that's probably a question for the agency generally. I think that's enough for now.
Thank you. Dr. Ginsburg? Thanks. Gary Ginsburg here again. I think that the discrepancy that we were pointing out in our comments regarding tables G2 and G4 on the commercial side got answered yesterday, unless I heard that wrong. EPA clarified that I believe the higher estimate for the commercial was the one that should have been reflected in both tables. And so I think we didn't hear that when we wrote our comments, but the EPA may want to clarify in response to this particular question. Again, for the record, just what are the right numbers that they meant for us to be reviewing in tables G2 and G4? And what was the right percentile of the sheds data that they were using? Was it the 90th or the 99th percentile? Because I think there was confusion about that as well. I guess going back to some of my earlier comments and thinking about the East Liverpool example, which is probably not the best way to try to ground truth down the drain releases for the things that Dr. Heiger-Bernays already talked about. There may be a much different approach to actually getting POTW data for a POTW that's not known to have industrial source water releases into it or processed water releases into it, and trying to ground truth just how much 1,4-dioxane is coming through that type of POTW versus a POTW that does have a number of different types of industrial source water or processed water releases into it. And you might start getting a closer to the source information rather than, the drinking water intake in East Liverpool with a whole lot of assumptions going into what are those down the drain consumer and commercial uses, and assuming that the BASF plant is not releasing 1,4-dioxane, and just there's a lot more that has to be assumed as opposed to going closer to the actual release point. for POTW if EPA used that kind of data. Thank you.
Okay, Dr. Ginsburg, if you want to send me updated comments, that's fine. Or if you've stated something you want included in the record in the document here, that would be great. Okay, I'll move on to Dr. Miglino.
Hi, Andrew Miglino. I would say that I think Dr. Heiger-Bernays summarized my comments pretty thoroughly. I do agree with Gary that Dr. Ginsburg, that the discrepancy in G2 and G4 tables, I believe that was covered this morning. So just clarifying that in the final document, I think would satisfy that issue. I have nothing else to add.
Thank you. I apologize. I was in the classroom this morning and I didn't hear the clarification. So I apologize. This is Wendy Heiger-Bernays. I apologize. And I don't think that Dr. Rumpler is here. Is he?
He is not.
Okay. That about closes out this question, unless there are other.
So from the whole committee, so thank you, Dr. Heiger-Bernays. From the rest of the committee, are there comments regarding question 2.2? Or comments, questions or comments? All right, if there are none, we can go on to charge question 2.3A.
Hi, this is Brian Groza, and I'm going to read charge question 2.3a. EPA developed an aggregate probabilistic model to estimate surface water concentrations as described in section 2.3.1 and appendix G.2.3. Please comment on the strengths and uncertainties of the aggregate probabilistic model.
All right, thank you. And the lead discussant for this question is Dr. Rubin. Thank you, Dr. Cobb. Rainbow Rubin. The EWISRD XL model was developed to account for 1,4-dioxane in aggregate. It includes industrial releases, down the drain, and background. It applies a steady state mass balance approach to estimate surface water concentrations and relative contributions from different sources from a single point on a stream at a single point in time. The model aims to provide nationally representative distribution of estimated surface water concentrations of 1,4-dioxane. The assumptions made based on the physical chemistry properties and fate characteristics are valid and appear to represent the behavior of the chemical accurately. Overall model framework as presented in Appendix Figure G2 appears to be well designed and comprehensive. However, reviewers indicate some components which introduce uncertainty with respect to DDT contributions, validation modeling runs, aggregate exposures, flow variability, and data gaps. The limitations and uncertainties to be discussed include the following specific comments. Number 1, DTD contributions. As stated under step 1, background contributions, DDT calculations are too uncertain to populate the model with a starting background concentration. And so the nearest upstream PWS monitoring data are used to simulate background. While this may be a good approach by admitting the uncertainties in DDT modeling, it is questionable that the way DDT modeling is added into the aggregate model at any stage or particular reaches of the river provides any more confidence. DTD releases are based upon EPA's estimates of local population and SHED's estimates of end user amounts across such a population. The one validation exercise for DDT loading, East Liverpool, Ohio,
is very limited, and as pointed out in another response, there are numerous uncertainties in the way DDT loadings are calculated and represented in appendix tables G2 and G4. A major point is that without knowing the specific locations of POTWs and the population served by these POTWs, it's very difficult to estimate DTD contributions to a particular river system. Number 2, validation modeling runs. The North Carolina case study was meant to ground truth the overall modeling of inputs, river flow dilution, etc. However, Appendix G4 or main text figure 214 shows that the modeled concentrations at the Brunswick intake hover around the mean AWQR reports n equals 5, but does not come close to the maximum concentrations in at least 2 of the years. Thus, this case study shows that the aggregate model using mean flows and the 250-day per year industrial release is reasonable for estimating mean concentrations, but not maximums. This has particular implications for shorter term exposures and acute endpoints, but is of less concern for chronic exposures and cancer risk. The East Liverpool, Ohio case study simulates a PWS intake under the influence of background as measured at an upstream public water supply, an industrial facility, BASF Corp, and by the surrounding population DDT releases. For commercial DDT releases, it appears that three of the product categories were simulated for commercial releases: dish soap, dishwasher detergent, surface cleaner, but not for laundry detergent, etc. And so it's unclear why some types of DDT releases are included in the scenario, but not others. Further, according to Appendix Table E1, since the number of facilities, e.g. restaurants, buildings with janitorial services, is unknown for East Liverpool, a bounding assumption involving all the companies in the NAICS code nationally were applied to the East Liverpool case study, i.e. 773,851 sites for companies that use dish soap, Table E1. This is an unrealistic modeling assumption, and the fact that the aggregate model estimate for the drinking water intake is only 0.61 parts per billion would suggest that these types of DDT releases do not lead to large impacts on a river as large as the Ohio River. The fact that an overshoot of the sampling data was obtained is not surprising given the nature of the upper bound assumptions used. The quantitative inputs to the Ohio River come from cleaners is unclear in Appendix Table E3. Are the results per individual releasing company or for all companies in aggregate? Are the results on an annual basis and divided by 250 to get the daily release rate? Regarding the validation exercise, there is no location identified for the POTWs that discharge into the Ohio River upstream of the East Liverpool PWS intake, and we don't know what percentage of the population or commercial DDT releases would be feeding into the river via POTW and what percentage would be on septic and not making it to the river. There are many census designated localities along the Ohio River shown in Appendix Figure G6, but how many have POTW releases to the river? If none or very few POTW outfalls occur within this stretch of river, then this run of the aggregate model may be insensitive to DDT inputs. Another limitation is that there were no detections of 1,4-dioxane at the East Liverpool PWS intake out of the 4 AWQR sampling results. And so the modeled concentration, 0.61 parts per billion, is without a quantified value for comparison. While this appears to be an overestimate, this case study doesn't prove that DTD releases via POTWs wouldn't have made a measurable contribution had there been enough information
on where the POTW releases exist and the population businesses they served. One also doesn't know how well this one case study captures the range of DTD to surface water impacts that are possible across the country. EPA's own assessment of this case study, Appendix Table E4 and E10, is that, quote, EPA has concluded that the weight of the scientific evidence for this assessment is slight, unquote, with regards to the inputs from surface cleaners, dish soap, and dishwashing detergent. The reliance on a single location, East Liverpool, Ohio, to determine the usage and or discharge for several OES categories carries a substantial amount of uncertainty with it. And it is not clear why this location was selected over any other location or range of locations. As EPA notes on line 1791 through 1792, quote, it is uncertain whether the release estimates generated from this case study are applicable to other areas of the country, end quote. From the 2022 RE, EPA does not appear to validate this use is valid or even reasonable. If EPA moves forward with the aggregate probabilistic model, it should reevaluate this assumption, and if it cannot be validated as appropriate, adopt a range or distribution of values approach as it does with other aggregate probabilistic model parameters. The Duck River, Tennessee case study is also very limited. Data from the Columbia, Tennessee PWS was used to compare DTD estimates for populations along the Duck River upstream of Columbia. And since there are no known industrial releases to the river in this reach, the 1,4-dioxane detections are assumed to be due to DTD. While Appendix Figure E5 shows towns along the river, whether these towns have POTW releases into the river or its tributaries is not described, nor the population that would be served by these releases. Once again, this validation exercise may be insensitive to DDT releases if there are few POTWs releasing into the stretch of river. Another limitation is that the case study is based upon only 4 measurements at the PWS intake. Number 3 of 5. Aggregate exposure. It appears that the aggregate approach described in the 2022 RE does not completely aggregate all sources in a watershed. For example, the discussion in Appendix G.2.3 refers to 3 separate analyses. 1, background sources plus facility releases. Number 2, DTD, commercial and non-commercial releases. Number 3, hydraulic fracturing. These 3 analyses are not combined and therefore do not appear to give the whole picture of potential exposure concentrations. Therefore, it's not certain that the aggregate probabilistic model provides for fully informed decision-making. Number 4, flow variability. The monthly average flow data from the NHD plus and background concentration based on stream order of releasing facility derived from monitoring data is appropriate for many conditions. Although ideally there are more flow scenarios considered to account for low flow, drought, and climate change conditions. A range of values for flow conditions is recommended to account for low flow conditions in which chemical concentrations are higher. Number 5, data gaps. Uncertainty is introduced through the insufficient data from TRI and DMR, considering the widespread commercial use of carcinogens and endocrine disrupting chemicals that have high biological potency in exceedingly small amounts. And it's scientifically supported to address this data gap by widening reporting requirements to below 500 pounds. Uncertainty is also introduced by using non-commercial values to estimate commercial DDT loading values. Using the 99th percentile of household DDT would approximate commercial DDT may underestimate loading. Additional comments came from the chair of the committee. In line 1872, the ordinate label should indicate, quote, detected concentrations. In line 1878, the ordinate label does not impart sufficient information to determine what is depicted in the figure. And in 1958,
in line 1958, data in this map may be misleading. Unless water is sampled downstream of a known source, there should be no detectable 1,4-dioxane. It would be more helpful to show concentrations in samples within UCMR3s that are within a few miles downstream of a likely 1,4-dioxane source. And that is all I have, and I am happy to call on my discussants.
Thank you.
Dr. Ginsburg. I have nothing to add. Thank you for that summary.
Thank you. Dr. Miglino.
I also have nothing to add. Thank you as well.
Thank you. And Dr. Reif.
Nothing to add. Thank you.
Thank you. And is Dr. Bennett here? Dr. Bennett.
I'm here. Yeah, thank you. No, I don't think I have any. Yeah, I don't have anything additional to add.
Thank you. I'll hand it back over to you, Dr. Cobb.
Okay, great. Thank you very much. I see one hand from Dr. Ottinger.
That was a really encompassing and excellent overview. And my only comment is, given that I've done many years of research with the endocrine disruptors, I would caution that can open a really big can of worms. So if the EPA decides to go down that path, perhaps more discussion would be needed to figure out how to properly incorporate that.
Yes. Right. Other comments? Okay, seeing none, it is just about time for a break anyway. We are very far into tomorrow already. I want to do a little bit of checking here. I believe Dr. Reif said that he has a time conflict right now with a class or meeting that he has to attend. I was going to check with Dr. Bennett to see if question 2.3C was reasonably ready to proceed or if we need to postpone that till tomorrow.
Yeah, I'm not sure I'm reasonably ready to proceed on that. We're much farther ahead than I expected us to be. So I've got to kind of and I've got quite a bit of feedback from a couple of the respondents. So I want to make sure I capture it properly. Okay.
And then Dr. Voorhees is not here today. Is that correct? So I think that one is, the next one's not a possibility. Question 2.4a, Dr. Potter, is that perhaps ready enough for today, or do you need time till tomorrow?
Get in here. We could go today. I haven't quite polished the language on it, but if we need to, fill in the rest of the day, I'd give it a shot.
Do you feel comfortable with that, or do you think we're going to be rushing you if we skip ahead to that question today?
Well, gee, if you're asking me, can I defer it till tomorrow morning? And I say yes.
Okay.
But
yeah,
no,
okay.
I think we could. No, seriously, I think we could. I think I can do justice to the material, but so I guess I'm expressing my ambivalence here.
Okay. Yeah, I
apologize for the time issue. I know that Dr. Voorhees actually added comments to both of these next two questions, so I know he's planning to be here, I think, tomorrow. So it'd be great if he can take part in today's discussion on those two that he's involved with.
That's all good. So I think if it's okay with the discussants on 2.4a, that's Dr. Potter, Clark, Fox, Graham, and Hager-Bernays. We'll go to 2.4A before the close today. And then if we need to circle back to that tomorrow, we certainly can. Is that okay?
Sounds good to me, Dr. Cobb.
All right. So let's now take a break. Let's take a 15-minute break and be back. What would that be? Well, 15 minutes from now, the clock will start. Let's go ahead and take the full 15-minute break since we got plenty of stuff done, and then we'll come back and pick up with 2.4A for the agency, so you can get the slide ready. All right. Thanks, folks, and we'll see you back in about 15 minutes. All right, looks like we are back. So we were talking about moving around our charge questions a little bit, and we were going to go to charge question 2.4.A, which is technically at the end of tomorrow's agenda. Dr. Potter was going to cover that as the lead discussant for our committee. And so if the EPA can read charge question 2.4.A into the record. Is there anybody there from EPA?
Hi, this is Brian Groza. And before we read this question, would it be appropriate to offer a point of clarification at this time?
Surely.
Okay. Yeah, just with regards to the last charge question, we noticed there was potentially some confusion between sections that I wanted to help clear up as you all move forward. First, to point out that as noted, there were multiple case studies completed to assess the application of the eWizard model. And we highlight the Duck River example in Columbia, Tennessee as one that has a sole input. The only input is expected to be down the drain loading in that scenario, and there were detected concentrations at the downstream end to differentiate from the Liverpool, Ohio case study, which is, and to note that was discussed in Appendix E, where some values were used from that case study, but what's described in Appendix E is part of a different analysis that's separate from the probabilistic model in that case study. That I just wanted to note that it was answering a different question. I have Franklin here to speak to that a little as well.
This is Franklin Hall. Sorry, bad habit. This is Franklin Hall. Just to sort of follow up on what Brian just said. So in the engineering assessment, we did use a certain component of data that is in the SHEDS HT model, and that was to determine the distribution of users or population of users, commercial users, for our dish soap OES, or condition of use. So we believe that there may be some confusion in the fact that for the engineering assessment, we used a very small part, basically some parameters from within the model, the SHEDS HT model, whereas the work that Brian has done was the actual modeling itself. And so we think that by making some clarifying statements in the corresponding sections of the engineering assessment, I think they may provide the distinction if needed for clarity so that that the confusion doesn't occur in the future.
That sounds like a good explanation to me. For those who were just responding to the previous charge question, does that seem reasonable to you? That was Dr. Rubin, Bennett, Ginsburg, and McGlino, and Reif, if he's still here.
I was just hunting for my unmute button. This is Dr. McGlino. That satisfies me, I think. Of course, it depends on what the final language says, whether it actually clarifies. But yeah, that approach at least seems to make sense.
Yeah, the devil is always in the detail, isn't it? So I think
I agree. I would welcome seeing the revised language. This is Gary Ginsburg.
Thank you. Okay, if there are no other comments, glad we got that clarified. And now we can read charge question 2.4 into the record, 2.4a.
Okay, this is Brian Groza, and I'm going to read charge question 2.4a. EPA estimated the impact of generic assumptions about the degree of dilution on the overall distribution of concentrations and risks from individual facility releases. Please comment on the strengths and uncertainties of the generalized dilution estimates presented in Figure 5.4. As part of this discussion, please comment on the strengths and uncertainties around EPA's assumption that in some locations, minimal dilution may occur between the point of 1,4-dioxane release and the location of the drinking water intakes.
Thank you. And Dr. Potter is our lead discussant.
Okay. Excuse me. Hello, this is Thomas Potter. First, I'd like to acknowledge the associate discussions on this question. Cassie Clark, Mary Fox, let's see, Dr. Graham and Dr. Hager Bernays. And I want to apologize in advance. All of you had sent in written comments. I haven't had a chance to blend them into the text at this point, but we'll do as we get to a final form and putting together the document. So I will read your comments at the end. I think we're all in general agreement about what we think the agency has presented, particularly with regard to the dilution question. First, so I'll start out by saying EPA was working at evaluating exposures from drinking water consumption, primarily looking at, in this case, surface water, streams and rivers. The agency, at least in the text, indicated that to the best extent possible, they used measured surface and drinking water dioxane concentrations. And they also used models to predict drinking water concentrations. There were a number of conservative assumptions that were made in terms of exposure. One of them being that essentially there's no dilution from a dioxane discharge to its intake point at a drinking water treatment plant. And secondly, that there's essentially no attenuation during transport, attenuation being biodegradation or photolysis or something to that effect. So some very conservative assumptions were made. Nevertheless, the outcomes in terms of cancer risks seem to be relatively modest. Again, we can have some dialogue on that amongst the discussants. I'd like to start out by first saying that the agency has emphasized their desire to use the monitoring data, and indeed they were successfully identified a very large data set. I think I heard earlier today there was something like 14,000 measurements that were in a database. And so that's certainly impressive. And indeed, I think all of us would love to as we go forth on assessing risk, a measured concentration certainly is worthy of respect, and taking note, especially in terms of weighting in determining actual exposures. The problem, of course, with monitoring, as we probably, any of us who have been in the business for a long period of time, particularly in environmental monitoring, is that oftentimes measurements are below limits of detection or reporting limits or practical limits of quantitation. And that certainly was the case with the data set that was assembled by the agency. Something like only 10% of the values were so-called detects. And again, those of us who've been in the business of dealing with monitoring data over the years recognize that when you have highly censored data sets, i.e. when a large percentage of the values are below some detection limit or a reporting limit or quantitation limit, it makes the statistical assessment of the data challenging. This has been covered extensively in the literature, and I won't get into any great detail on that, except to say that despite our best intentions in terms of wanting to use monitoring data to inform the risk assessment, it is challenging in terms of finding appropriate statistical tools that allow taking into account the large number of values that are below method reporting limits or detection limits. I have several references that I'll include in the document that will help hopefully provide some insight on that. So that gets me back to something I heard earlier today from Dr. Jajak, and I thank you for bringing this up. Even though we'd like to think that we're as a chemist, and I consider myself to be a chemist, we're strongly supportive of measurement. Modeling is often the way to go in terms of trying to get a handle on what are potential exposures and doing some range finding on that. And the agency, I think, recognized that as well. And so they went through a series of modeling exercises looking at discharges, either potentially from the industrial sources or from sewage treatment facilities, and using those as point sources, discharge into streams or rivers, and then making assessments with regard to concentrations at downstream intakes for drinking water. And of course, again, these are quite complex in terms of the actual geography of the situation. It's hard to come up with a specific location where each scenario may be met, but I think the agency did a good job of setting out what are plausible limits in terms of, particularly in terms of dilution. Again, this essentially assumed there's no attenuation. And so the assumptions were highly conservative, essentially no dilution. There's a discharge from an industrial facility or a sewage treatment facility, and it's not diluted at all as it moves downstream. It's taken up into the drinking water treatment facility and delivered to the public. There's some basis for indicating that indeed may be a scenario that's observed, particularly in some parts of the country, especially when you have low flow conditions. And here I want to note some excellent work that was done by a group at Arizona State University. They have a number of publications dealing with the issue of, let me see if I got this right here. de facto reuse in our nation's drinking water supply. And so what does de facto reuse means? It means that somebody is discharging treated wastewater upstream of our drinking water intake. We may not necessarily know that. Nevertheless, that apparently occurs quite frequently across the country, and is certainly a function of local climate that relates to stream flow, et cetera. But generally, areas where you have low flows during certain times of year, you tend to have relatively high percentages of de facto reuse of treated sewage. And it's not necessarily something the folks in the water supply district want to hear. There's been some interesting work done in that area as well. One of the things that group at ASU did is develop a model called DRINKS. And the DRINKS acronym fits this de facto reuse in our nation's consumable supply. It's looks very similar to what the agency did in terms of using their hydrographic data that was described in some of the earlier questions, and coming and reaching conclusions relative to the degree of dilution that may occur. Indeed, there are certain scenarios, particularly in the great old state of Texas. There's a very nice paper indicating that you can essentially get the folks downstream or taking up treated sewage and putting it back into the drinking water system. So essentially you have that zero dilution conservative assessment seems to hold in some areas of the country, particularly for small streams and facilities where surface water is limited. And so that, to answer the agency's question on this, indeed, there is some basis for concluding that there are situations that do exist. What their relative percentages are is difficult to assess at this point, but there are situations that do exist where you essentially have no dilution from either an industrial discharge or a sewage treatment plant discharge. Further assessment, looking at a greater distribution of facilities across the country. Again, this is work done by Rice and Westerhoff. They conclude that basically somewhere around a 1% dilution rate seems realistic and appropriate across the board. So again, the agency looked at the 1% value, compared that to the 100% value in terms of relative amounts of dilution. I think first off, there's a very conservative estimate of no dilution, but the 1% dilution also indicates that the risks are comparable. So what's interesting is that there didn't appear to be a lot of sensitivity there, and that's maybe something that we need to dig into a little bit further. And so to sum up, generally, I think that the agency has done a reasonable job of looking at the potential for dilution, both in an extreme case, essentially no dilution, in what would be a normal case, somewhere around 1% of the source of the drinking water supply to the drinking water supply is about 99% surface water and 1% treated sewage. So one thing that I would strongly recommend is the agency take a hard look at this DRINKS model. Perhaps you're familiar with it already. Seems to be, again, something that looks very similar to what the agency did in terms of assessing the questions about dilution. So let me just wrap up here by highlighting some of the comments that are received from some of the associate discussants, and they'll get a chance to talk about that as we go forward here. One point that was made was accounting for dilution of point of source releases still yielded cancer risks in the 1 to 1 in a million associated with drinking water for some areas, which is considered above the threshold for lifetime risk. So that was a concern, even though there is some potential for dilution. We still potentially exceed in some higher end of the distribution lifetime cancer risks. Another point that says assessment of minimal dilution between releases in location of drinking water takes us. Senator says, I'm concerned that EPA did not include a high flow condition in the modeling. I guess high flow would be more dilution and perhaps lower risk. So I'm not sure where that was headed. Perhaps we can explore that a little bit further. And the other individual, it says that, and I think across the board, and I think we've heard that with other questions, we're concerned about extreme events and potential impacts of climate change, periodic droughts, flash flooding, and all the other issues that relate to dilution, transport, and potential exposure. Some of the other points, weaknesses and uncertainties by minimally diluting the predicted exposures and subsequent risks are overestimated, at least from known releases. So there's a high degree of conservatism there. And again, another point being climate is an uncertain variable as we move on to the future. So I guess we'll wrap it up there, and I'd like to we can call on the associate discussions and see if they have some more that they want to fill in on it.
All right, thank you very much. So our other discussants, first of all, Dr. Clark.
Hi, yes, this is Cassie Clark. I think Dr. Potter summarized really the bulk of what my concerns were. I have some additional comments for the dilution factor, but I think I'll save those for our discussion of charge question 2.4b tomorrow in the groundwater section.
Thank you. Dr. Fox.
Nothing to add.
Okay. Dr. Graham.
This is Dr. Cynthia Graham. And I just want to preface this. This is outside of my knowledge base, but I had no idea where they came up with that 1% dilution that they used. I heard from Dr. Potter that in fact someone, there is references to that number. So that was basically my concern, where they come up with this 1% to use, even though it didn't really change the risk that much. So other than that,
yeah, it's described in, yeah. I didn't mean to cut you off there. I'll just say it's described in the couple of the publications by the ASU group, Rice and Westerhoff in particular. And again, I'll include those references in the draft document that I sent out to everybody.
And that was Dr. Potter.
Yes. And I was just going to say, I think Dr. Potter did an excellent job in summarizing the concerns and the response.
Okay, thank you, Dr. Graham. Dr. Heiger-Bernays.
Wendy Heiger-Bernays, I have no additional comments. Thank you, Dr. Potter, for teaching us a little bit more.
Okay, thanks to everyone. One thing I would point out, this is George Cobb, is that the concern about conservatism is one that we should be aware of. However, in the paucity of data that we have, conservatism is where the agency should be going, because until there are data to actually inform the decision, measured data, then you really do have to err on the side of conservatism to a large degree. That's why I've called for data for so many years to get us out of this conundrum. Dr. Chase.
Well, I agree with everything you're saying. I struggle every time I hear the word conservative. This has been used not just by EPA, but by many groups, but it means different things. If you're talking about, gee, I'm going to be conservative about something, it may mean that you're picking a value that's lower, or maybe it means you're picking some value that's higher. And really what it expresses is a bias. So it's not really a scientific statement. I mean, so if the point of the evaluation or the choice or whatever is to pick an upper end or a lower end value, I think the agency would be well served to just say that and get away from the word conservative. Looking back in older documents as well, you can see that words like that stand as a point of confusion because to some degree, the concept of conservative is a temporary situation. It's a perspective, if you will, and perspectives change with time. So I would, this is just a personal editorial point, but I feel very strongly that we should never use that word.
So yeah, I understand what you're saying, and maybe you can substitute the word protective when I was speaking just a second ago. Mr. Ross.
Yeah, just in regard to the last comment, I'm not sure this helps any, but I used to do, I still do a lot of worker education on occupational safety and health issues. The hardest thing is making some of this fairly complicated material and rendering it in plain language. But for what it's worth, the words we use is health conservative, with the idea that, you know, this is conservative in the sense that we're trying to protect your health. I have one other comment about this whole area too, very quickly, if that's okay.
Certainly.
I was struck, and this is a very general comment, but I was struck in the document by the fact that much of what was in it was health conservative, like the assumption we've talked about in this charge question, that there's essentially no dilution. But other parts of it seem to me to be not health conservative. And I'll give one example. The assumption, and I think it's Appendix F, I'd have to go back and look at it, that people who occupationally use cleaning products in a for example, commercial cleaning situation, do so for 4 hours a day for half a shift. And at least in my experience, that can be quite wrong. And many workers use these products for actually more than 8 hours a day. Overtime has really exploded in this country ever since the 1960s, when it became cheaper to pay benefits. I'm sorry, it became cheaper to pay for time and a half to workers than to pay benefits for an additional worker. And I think, I don't have any data on this, but I think that situation has only been exacerbated since the pandemic, as a lot of enterprises are short of labor. So I know situations where people may be janitors or may even be house cleaners, and they use commercial cleaning products for not just 8 hours a day, but for 12 hours a day, sometimes for 5 days a week. So that seemed to me So assuming that it's 4 hours a day, 5 days a week, does not seem to be health conservative. So EPA went kind of both ways in this document.
That's a good comment, and please make sure that that comment does get to the appropriate person reviewing. And I'm not looking at the exact, but the appropriate person reviewing the worker exposures.
Yeah.
Okay, so we are pretty much at a stopping point. We're very much ahead of schedule. I do want to point out to the members of the committee that the contractors for the Zoom that we're on have the ability to set up breakout rooms for different discussant groups. Should any of the discussant groups want to spend the next half an hour or so trying to get things ready for tomorrow, or even revisiting or refining things that you're working on now. So I guess just to start, do any of the groups 2.3B, C, or D want to try to get together in a breakout group to discuss what needs to be presented tomorrow? Or in a breakout room, I guess I should say. I'm seeing no takers. And Allah is smiling because that means he doesn't have to worry with getting them set up.
That's an easy thing.
George, this is Ken Portier. I think most of us are more used to asynchronous communications. You know, I send the version out, they send me comments back. And that seems to work better than trying to get in a group and group right, which is very difficult to do.
Yeah, I thought that perhaps if there was enough writing done, you could quickly say, hey, these things are good, these things aren't, and get it all done pretty quick. But I also understand everybody is probably tired. I simply wanted the opportunity to be available to anyone that wanted it. So if we have no further comments, and we have no one wanting a breakout room, I'm prepared to adjourn for the day and come back tomorrow, where we will have start with question 2.3b. If the agency can be ready to read that into the record, and Dr. Reif can be prepared to lead that discussion. I should also point out, we will circle back and make sure there are no points that got left undone or unsaid today. And then we'll proceed with that question. So, any other things before we close? Allah, do you have anything that you need to say or want to say?
Well, I just want to thank everyone for the discussions today. It was like very exciting discussions and very informative, and also all the response and the questions that were read from the EPA presenters. Thank you, George, for chairing this session today, and hope we see everyone tomorrow morning at 10 o'clock Eastern time. And that's all. The meeting is adjourned.
Thank you, everyone.
Thank you.
Thank you.
Thanks.
Bye-bye.
Unmute. I'm unmuted.
Oh, wait a minute.
I'm here. So I want to go over some of the game plan